Late at night, under a moonless sky, the world falls silent. Above you, an infinity of stars unfolds, tiny, brilliant lights scattered on a canvas of perfect darkness. The longer you gaze, the more stars seem to appear, as if the universe is slowly revealing itself one sparkle at a time. In the absence of city lights, the Milky Way arches overhead as a pale, glowing river of stars, countless distant suns whose combined light forms a ghostly band across the sky. There is a hush, a sense of timelessness, as you stand beneath this cosmic vista that countless generations before you have admired. Each star twinkles with steady, ancient light. Though they appear eternal and unchanging, the glow you see began its journey ages ago, years, decades, even centuries in the past. Some of those stars are so far away that their light has traveled thousands of years to reach your eyes. When you look up, you are literally peering into the past, seeing the sky as it was when that starlight first set out across space. It's a gentle reminder of how vast the universe is, and how long the stars have been shining in the darkness. On a clear night like this, far from any human settlement, you might see 2,000 or 3,000 stars sprinkled above. They freckle the heavens in no obvious order, yet patterns emerge if you let your imagination connect the dots. There, you might notice a curve of stars that forms a dipping ladle, or a line of 3 bright stars in a row like a celestial belt. Among them, a few brighter points stand out and do not twinkle as much. Those are planets wandering among the stars, distant worlds reflecting the sun's glow. But most of those lights are true stars, nuclear furnaces trillions of miles away, each one a beacon in the vast dark. Now and then, a streak of light silently races across the sky, a shooting star, here for an instant and gone. It isn't a star at all, but a tiny grain of cosmic dust burning up as it dives into Earth's atmosphere. Still, when we see that sudden flash, it feels magical. Many of us can't help but whisper a wish, keeping an ageless human tradition, as if the cosmos might be listening. In those moments, under that sprinkle of ancient starlight, you might feel a profound connection to something larger than yourself. Beneath the night sky, time seems to slow. The clamour of daily life fades away. You feel the cool air and the gentle earth underfoot, and above, only the endless stars. The universe displays its grandeur in silence, needing no words. It invites you to ponder big questions. How far do those stars go? What lies out there beyond our sight? It stirs a sense of wonder, a curiosity that humans have felt for as long as we've existed. We share this view with our ancestors, who looked up at the same stars ages ago, seeking patterns and meaning in the lights above. That ancient curiosity is our starting point for a journey through the cosmos, a journey that begins simply beneath the night sky. For as long as humans have walked the earth, we have turned our eyes to the stars for guidance and inspiration. In the deep past, before history was written, our ancestors watched the skies intently. The rising of certain stars at dawn told them when seasons were changing, when to plant crops or prepare for winter's chill. The night sky was their calendar and their clock. Patterns in the heavens marked the passage of time long before any human-made calendars existed. As generations passed, people learned to predict the return of those patterns, the appearance of a particular bright star on the horizon, or the way the star groups shifted with the seasons. In ancient Mesopotamia, around 5,000 or 6,000 years ago, priests and scholars climbed tall ziggurats, step pyramids of brick, to study the night sky. They carefully noted the movements of the wandering stars that we now know as planets. They recorded eclipses and the cyclic appearances of Venus, believing these celestial events were messages from the gods. Hundreds of miles away in Egypt, great pyramids and temples were built in alignment with the heavens. Egyptian priests noticed that just before the annual Nile floods, a bright star, Sirius, rose at dawn after a long absence. They came to rely on this star's reappearance to herald the life-giving floods, tying the rhythms of the river to the rhythms of the cosmos. Far to the east in ancient China, royal astronomers scanned the skies from palace observatories. They documented new stars, comets with glowing tails, and lunar eclipses with meticulous care. To them, an unexpected event in the heavens, like a new star suddenly appearing, could signal the rise or fall of an emperor. Stargazing was not merely curiosity, it was a matter of state. Meanwhile, on the other side of the world, the Maya of Central America built observatories atop their pyramids. One such structure, a round tower now called El Caracol, has windows aligned to capture the light of the setting sun on specific days. The Maya charted the cycles of Venus and the motions of the moon, weaving them into one of the most complex calendars ever devised. For these civilizations, the sky was a grand clock and a cosmic stage where gods and heroes played out dramas that guided earthly life. Not all stargazing happened from towers and temples. Imagine a sailor in the ancient Pacific navigating a canoe across open ocean hundreds of miles from any shore. With no compass, they relied on the stars. The people of Polynesia learned the pattern of stars like a living map. Each night, familiar star clusters would rise in the east and set in the west. By knowing which stars should be overhead or on the horizon at a given time, these navigators could hold their course over vast distances. Similarly, travelers crossing deserts at night followed the heavens to find their way. One star, Polaris, the North Star, stays almost fixed in the northern sky. To people in the northern hemisphere, Polaris became a reliable beacon, always indicating north. Many a journey over sea or sand was guided by that steady star and its constellations. Beyond practical needs, ancient people found meaning and comfort in the stars. They looked up and felt the sky was telling a story. Perhaps they saw the outline of a great hunter chasing elusive prey, or a giant bear eternally lumbering among the stars. Different cultures wove different tales, but almost all saw shapes in the stellar scatter. The night sky became a rich tapestry of myth and legend, populated by heroes, monsters, gods, and animals of every kind. These constellations, as we call them, served as both storybook and navigation chart. By memorizing star patterns, people could pass on knowledge of seasons and directions wrapped in memorable tales. And so, gazing upward, the ancient stargazers saw not just a physical sky of lights, but a sky alive with stories, a cosmic tapestry where every dot of light had a name and a meaning. This union of observation and imagination shaped how humans understood the cosmos for millennia to come. When we connect the stars with lines in our mind, familiar shapes appear. It's a bit like finding pictures in clouds, except these starry pictures became legends shining in the night. Every culture drew its own sky maps, turning random speckles of light into heroes, creatures, and gods. On a clear night, the sky becomes a grand storyboard of human imagination, filled with tales of creation, adventure, and destiny. High above, 3 bright stars, in a neat row, form the belt of Orion, one of the most famous constellations. The ancient Greeks saw Orion as a mighty hunter outlined in the sky, raising his club and shield. They told how he boasted that no animal on earth could escape him, which angered the gods. In revenge, a small scorpion was sent to sting him. The hunter and the scorpion both were placed among the stars. To this day, Orion and the constellation Scorpius appear on opposite sides of the sky. When the scorpion rises, Orion sets, as if the hunter still flees from the scorpion's eternal chase. Not far from Orion's glittering belt lies a V-shaped cluster of stars, forming the face of Taurus, the bull. In Greek myth, this bull was Zeus in disguise, carrying a princess named Europa across the sea. Nearby, a tiny cluster of 7 stars called the Pleiades sparkles like a little teaspoon of light. The Greeks imagined them as 7 sisters placed in the sky to escape Orion's pursuit. Many cultures saw something special in these stars. To the Kiowa people of North America, they were 7 young girls who escaped a bear by climbing a magic rock, a rock that grew into the sky to lift them to safety. Separated by oceans and centuries, people around the world all looked at this little cluster and wove stories about a group of 7 siblings shining together. Another striking pattern is the Big Dipper, which is part of a larger constellation called Ursa Major, the Great Bear. The dipper's bowl and handle are bright and easy to recognize. To the ancient Greeks, these stars formed a great bear forever circling the North Pole. One legend said the bear was once a woman named Callisto, whom Zeus placed in the sky for her protection. Yet other peoples envisioned very different shapes in these same stars. Some Native American storytellers also saw a bear in the dipper's bowl, with the 3 handle stars as hunters trailing it. Medieval Europeans saw a wagon or plough. In England, those stars are still called the plough. And in China, the same 7 stars were known as the Northern Dipper, seen as a celestial ladle scooping the nectar of immortality. Amazing how one pattern of stars can inspire such an array of legends around the world. Along the band of sky, where the sun, moon, and planets travel, the path called the ecliptic, lie the 12 constellations of the zodiac. Ancient civilizations paid special attention to these, since the sun and planets move through them over the year. Each zodiac sign carries its own legend. Aries the ram was said to be the golden ram of Greek lore, whose fleece became a hero's prize. Leo the lion was seen as the fierce Nemean lion defeated by Hercules. Sagittarius is the archer centaur, aiming his bow toward the heart of Scorpius. For many peoples, the changing positions of these constellations marked the turning of seasons and were thought to influence events on Earth. For millennia, humans believed the arrangements of stars and planets could directly affect our lives, a belief system we know as astrology. The zodiac constellations, linked to the time of year one was born, were thought to guide personality or fate. Even today, the symbols of the zodiac are widely recognized, a testament to how strongly those ancient star myths have endured. Mystical claims aside, the zodiac's constellations also served a practical purpose. They formed a celestial calendar. The rise of Aries at dawn might herald spring, while Orion's appearance in the evening signaled winter's approach. The stars helped people track seasonal time long before mechanical clocks. Legends of the night sky span every corner of the globe. In East Asia, for example, a love story is written among the summer stars. The star Vega, in the constellation Lyra, is known as the weaving maiden, and Altair in Aquila is the cowherd. Separated by the silvery river of the Milky Way, these 2 lovers are allowed to meet just once a year. According to Chinese law, A bridge of magpies forms across the sky on that night, the 7th night of the 7th lunar month, so the lovers can reunite. This romantic tale is celebrated in festivals like Kishi in China and Tanabata in Japan, showing how the stars became a stage for human hopes and love. Far in the southern hemisphere, under unfamiliar stars, Aboriginal Australians see a very different kind of constellation. Scattered dark clouds within the Milky Way's luminous band form the shape of a great MU across the sky. Instead of connecting stars, this constellation is traced by the dark gaps between them. The Coal Sack Nebula, near the Southern Cross, becomes the emu's head, and other starless patches outline its body and legs. To those Indigenous Australians, this cosmic emu is a powerful creator spirit, woven into dreamtime stories and tied to seasonal changes on Earth. No matter the culture, people found meaning and comfort in the stars overhead. They projected their fears, aspirations, and values onto the night sky, making the vast unknown feel intimate. Learning the constellations and their lore gave people a sense of orientation, both physical and spiritual. On dark nights around campfires, tales of Orion's bravery or the Seven Sisters' journey were shared, connecting communities to the cosmos and to each other. The night sky became a theatre of mythology, a mirror of humanity cast onto the stars. Yet for all these rich legends, the true nature of those glittering lights remained an even greater mystery. What were the stars, truly? Were they distant campfires of the gods, or holes in the firmament of heaven? No one knew for sure. It took centuries of scientific inquiry for us to begin to understand. Only with the invention of telescopes and the birth of modern astronomy did we learn that each star is a distant sun, a colossal, fiery sphere of plasma, far away in the cosmic dark. The science of starlight would reveal a reality even more wondrous than the ancient stories. As human curiosity pushed beyond myth into understanding, we finally began to unravel the real secrets of the stars. A star, stripped of myth, is something truly marvelous. A gigantic, glowing ball of gas held together by its own gravity. Our sun is one of these cosmic beacons, and every star you see in the night sky is another distant sun. For a long time, to human eyes, stars were just mysterious points of light. Only with science and careful observation did we grasp their true nature. We learned that stars are incredibly far away, so distant that their light takes years, centuries, or millennia to reach us. The nearest star beyond our solar system is more than 4 light-years away, meaning the light we see from it tonight began its journey over 4 years ago. Most stars are far farther still. To put it in perspective, a single light-year is about 9 trillion kilometers. Even the fastest spacecraft would take tens of thousands of years to travel that far. So when we gaze at the stars, we are peering across unimaginable gulfs of space and time. What makes these distant suns shine? The answer lies in their hearts. Deep inside a star, gravity's pressure is so tremendous that it crushes atoms together and forces them to fuse. In the core of a star like our Sun, hydrogen atoms merge into helium in a process called nuclear fusion. This releases an enormous amount of energy, pure starlight and heat. Every second, our Sun fuses roughly 600 million tons of hydrogen into helium. A small fraction of that mass is converted directly into energy, EMC2 at work, and that energy is what bathes our world in light and warmth. The same process is happening in stars all across the cosmos. Each star is a massive nuclear furnace, balanced between gravity, pulling inward, and the explosive pressure of heat, pushing outward. This balance can last for millions or billions of years, as the star steadily shines, turning matter into light. Not all stars are the same. In fact, they come in a dazzling variety of sizes, colours, and ages. Some stars are small and relatively cool, glowing with a subtle red hue. These red dwarf stars might be only a tenth the Sun's mass and give off only a tiny fraction of its light. They sip their nuclear fuel slowly and can burn for trillions of years, far longer than the universe's current age. Other stars are truly enormous and scorching hot, blazing with a bluish-white light that outshines our Sun by thousands of times. A blue-white O-type star lives fast and dies young, exhausting its fuel in only a few million years. In between are stars like our Sun, warm, yellow-white stars with moderate lifespans of around 10 billion years. The colour of a star is a clue to its temperature. Like metal heated in a fire, a cool star of about 3,000 degrees C appears reddish. A mid-temperature star around 6,000 degrees, like the Sun, glows yellow-white, and a scorching star of 20,000 to 30,000 degrees shines bluish-white. When you look up and notice some stars tinged orange or blue, you are seeing these temperature differences. Betelgeuse, the ruby-red star marking Orion's shoulder, is cooler and nearing the end of its life. In contrast, Rigel, Orion's blue-white foot, is much hotter and more massive. Each dot of colour in the night sky is telling us about its furnace within. Stars also differ greatly in brightness. The brightness we see from Earth depends on two things: how much light the star actually emits, and how far away it is. Some stars are intrinsically dim, cool red dwarfs that barely outshine a candle in cosmic terms. Yet if one lies relatively close to us, we might detect its faint glow with a telescope. In fact, the closest star beyond our Sun, Proxima Centauri, is a red dwarf so faint you need a telescope to spot it, even though it's just over 4 light-years away. On the other hand, some stars are intrinsically brilliant, shining tens of thousands of times brighter than the Sun. If such a star is even a few dozen light-years away, it can appear prominent in our sky. Sirius, the brightest star in Earth's night sky, owes its dazzle partly to being fairly close, about 8.6 light-years, and partly to being about 25 times more luminous than our Sun. Meanwhile, many of the stars visible only through powerful telescopes are extremely luminous giants. They're just so far across the galaxy that their light arrives as a faint whisper. By analysing starlight, scientists have unlocked many of the star's secrets. If we spread a star's light out into a rainbow spectrum, we find dark lines imprinted on it, a unique barcode for each star. These subtle fingerprints tell us what stars are made of. Astonishingly, we discovered that stars consist mostly of the lightest element, hydrogen, with helium as the next most abundant ingredient. There are also traces of heavier elements like carbon, oxygen, iron, calcium, the same elements found here on Earth and in our own bodies. In fact, the iron in your blood and the calcium in your bones were forged long ago in the cores of stars or during star explosions. We truly are made of stardust, connected to the cosmos at the chemical level. The same stellar fingerprints reveal a star's temperature and even its motion through space. If a star is moving toward or away from us, the lines in its spectrum shift slightly in colour, a phenomenon called the Doppler effect. Astronomers use this tiny shift to detect when a star is wobbling due to an orbiting planet, or to measure how fast stars and even galaxies are moving. By studying the subtle changes in starlight, we've measured the rotation of our galaxy and the expansion of the universe, and we've even discovered planets around far-off stars, all without leaving Earth. All this insight comes simply from decoding the light that reaches our telescopes. On a dark, moonless night, the combined glow of billions of distant stars forms the Milky Way, a faint band of light across the sky. Our own galaxy is a vast spiral containing perhaps a few 100 billion stars, of which our Sun is just one. Beyond our galaxy lie billions more galaxies, each with its own multitude of stars. The sheer number of stars truly defies imagination. There may be more stars in the observable universe than grains of sand on all Earth's beaches. The stars we individually see with the naked eye are only the nearest and brightest members of our galactic neighborhood. All the others blend into a distant haze, or are entirely too faint to perceive. When we look up, we're seeing just the tiniest sampling of an incredibly vast stellar tapestry. Interestingly, many of those pinpoints of light that appear solitary are not single stars at all. A great many stars come in pairs or even larger groups, bound together by gravity. These binary or multiple star systems orbit a common center, engaged in a slow gravitational dance. To the naked eye, they seem like one star, but a telescope may reveal two or more, perhaps one golden and one blue, each a sun in its own right, circling its companion. Our sun, in fact, is a bit unusual for being alone. Many sun-like stars have at least one partner, and in dense star clusters, hundreds or thousands of stars may be born together, glittering like a swarm of fireflies in the night. For instance, the Pleiades cluster we met earlier in myth is indeed an actual family of young stars born from the same cosmic cloud. Surrounding our galaxy, ancient globular clusters hold hundreds of thousands of stars packed in great spherical swarms, fossils from the early ages of the Milky Way. Scattered among the stars are signs of stellar birth and stellar death. Remember Orion's sword, which ancient sky watchers saw as part of the Great Hunter's outline. To the unaided eye, one star in that sword looks a bit fuzzy, as if out of focus. That is the Orion Nebula, an immense cloud of gas and dust where new stars are being born. About 1/300 light-years away, this stellar nursery glows with the light of young, hot stars that have just ignited inside it. Through a telescope, it appears as a luminous mist, with newborn stars twinkling within. A glimpse of creation in progress. Elsewhere, if you point a telescope at what appears to be a faint star, you might discover a ghostly shell of light around it, a sign that the star is dying. The Ring Nebula, in the constellation Lyra, for example, is not a solid ring at all, but a cloud of glowing gas cast off by a sun-like star at the end of its life. At its center lies a white dwarf, the small, hot core of the former star, shining like an ember through the expanding haze. Scenes like this are cosmic gravestones, marking where a star has gently bowed out. And there are other, far more violent endings to stellar life, titanic explosions that we will soon encounter as we explore how massive stars die. The more we discovered about stars, the deeper our sense of wonder grew. The reality of these suns, colossal nuclear engines forging the elements and lighting up the galaxy, is breathtaking. Knowing what they are doesn't make them less mysterious. If anything, it makes the night sky even more profound. Now when we step into the dark and gaze upward, we carry a double perspective. We feel the same awe that ancient humans did, and we also understand that each little star is a mighty sun, far beyond our reach. And yet, like everything in nature, stars are not eternal. They are born, they mature, and eventually they die. Their lives span millions or billions of years, and in their death, they sow the seeds of new beginnings. It is to the life and death of stars that we now turn, following the cosmic story from stellar cradle to grave. Stars are born, they live out their long lives, and eventually they die. But unlike living creatures, a star's lifespan stretches over millions or billions of years, and its birth and death are spectacular events. To trace the life cycle of stars, we begin in the vast dark clouds of cosmic gas and dust scattered throughout our galaxy. These are nebulae, the nurseries of stars. For ages, a nebula might drift quietly in space, cold and dark. But if something disturbs it, perhaps a shockwave from a distant explosion or the gravitational nudge of a passing star, parts of the cloud begin to clump together under gravity. As a clump grows denser, its gravity pulls in more and more material. Gas falls inward, and the clump's core grows hot and pressurized. This forming star, called a protostar, isn't yet hot enough to shine like a true star, but it's on its way. When the core of a protostar finally becomes hot and dense enough, nuclear fusion ignites. A star is born. A new light kindles in the darkness of its natal cloud. A newborn star is often surrounded by a whirling disk of leftover gas and dust, the ingredients for potential planets, moons, and asteroids. In time, that disk may coalesce into a family of worlds orbiting the star, as happened in our own solar system. Meanwhile, the young star settles into the long, steady phase of its life. During this period, the star fuses hydrogen into helium in its core, releasing energy. This is the main sequence stage, and for many stars, it lasts the bulk of their lifetime. A star like our Sun will remain in this stable burning phase for roughly 10 billion years. Smaller red dwarf stars, which burn their fuel slowly, can last even longer. In theory, hundreds of billions of years, far outliving any star that exists today. Massive stars, by contrast, burn through their fuel furiously and may live only a few million years. During the main sequence, a delicate balance is maintained. The outward pressure from fusion energy exactly counteracts the inward pull of gravity. But this equilibrium cannot last forever. Eventually, the star's core will run low on fuel, and the next act of its life story begins. When a star depletes the hydrogen in its core, its fate diverges depending on its mass. For a star about the size of our Sun, or smaller, running out of core hydrogen is the beginning of a gentle decline. With fusion slowing, the core can no longer resist gravity fully, so it contracts and heats up, while the star's outer layers puff outward. The star swells into a red giant. Its surface cools and reddens even as the core grows hotter inside. In the Sun's case, billions of years from now, it will expand into a red giant so large that it may engulf Mercury, Venus, and perhaps even Earth. In the core of that red giant, new fusion reactions will ignite, helium fusing into carbon and oxygen once temperatures become high enough. The star's life enters its autumn years, burning a different fuel in a much larger, more diffuse form. However, for a Sun-like star, this phase is relatively brief, lasting only a few 100 million years. Eventually, a star like the Sun can no longer sustain nuclear burning in its core. The fusion falters and finally stops, and the star becomes unstable. It begins to shed its outer layers into space. What remains at the center is an exposed core, extremely hot, but no longer generating energy. The cast-off outer layers expand outward, forming a glowing shell of gas. To an observer, this shell can appear as a beautiful ring or bubble of color, called a planetary nebula. Early astronomers coined that name because, in small telescopes, some of these gas shells resembled faint planetary disks. At the center of the expanding nebula lies the former core of the star, now a stellar ember known as a white dwarf. A white dwarf is incredibly dense. Imagine the mass of our sun compressed into a sphere the size of the Earth. It shines for a time with residual heat, a fading hot cinder of a once brilliant star. Over billions of years, the white dwarf will cool and dim, eventually becoming a cold, dark remnant, sometimes called a black dwarf, though none exist yet, given the young age of the universe. This is the quiet end for stars of modest size, a final ethereal display as a nebula, and then a long fade into darkness as the white dwarf cools. For the most massive stars, those many times heavier than the Sun, life and death play out on a more dramatic stage. A high-mass star races through its fuel at breakneck speed. It may shine millions of times brighter than a sun-like star, but in only a few million years, it exhausts the hydrogen in its core. When that happens, the star doesn't quietly drift into retirement. It fights back against gravity in a furious battle. The core contracts and grows hotter, igniting new fusion reactions of heavier elements. Hydrogen fusion stops in the core, though it may continue in a shell around the core, and the star begins burning through a succession of heavier fuels. The super-hot core fuses helium into carbon, then carbon into neon, oxygen, silicon, and so on, creating layers of elements like the layers of an onion. Each new fuel is consumed faster than the last. In a star perhaps 20 times the Sun's mass, the final stages of fusion, like burning oxygen and then silicon, might last only days or weeks. The star swells into a red or blue supergiant during this late phase, with a bloated outer envelope and an intensely hot core. Betelgeuse, the red supergiant star in Orion, is one such massive star nearing the end of its life. Its core is likely fusing elements heavier than helium right now, preparing for the final act. That final act comes when the core of a massive star turns to iron. Iron is like the ash of nuclear burning. Fusing iron doesn't release energy, it actually consumes it. So once an iron core forms, the star's nuclear engine effectively shuts down. With no outward pressure to support it, the iron core succumbs to gravity and collapses in on itself in a matter of seconds. The core implodes, and protons and electrons are crushed together into neutrons. An iron core that might have been as large as the Earth is reduced to a sphere only a few kilometers across. The collapse halts abruptly. The dense ball of neutrons resists further compression, and the infalling outer layers slam into this hard core. The rebound triggers a powerful shockwave. The star's outer layers are blown outward in a titanic explosion, a supernova. For a few brilliant weeks, a supernova can outshine an entire galaxy. It unleashes an immense wave of energy and rips the star apart. The debris of the star, heavy elements and glowing gas, hurtle outward as a rapidly expanding nebula. In the fury of the explosion, new elements are forged beyond iron: gold, silver, iodine, uranium, and many more. These precious elements, created in those fleeting moments of chaos, are flung into space, ready to become part of future stars, planets, and maybe even living beings. Even in recorded history, a supernova has been witnessed by humans. In 1054 AD, Chinese astronomers saw a guest star that shone in the daytime for weeks. We now know it was a star exploding. The supernova's gorgeous remnant is visible today as the Crab Nebula. Meanwhile, the collapsed core of the star remains, transformed by the supernova. If the original star was not too extreme in mass, that core becomes a neutron star, an object of mind-boggling density. A neutron star packs more mass than the Sun into a sphere only about 20 kilometers across. Its gravity is so intense that a teaspoon of neutron star material would weigh billions of tons on Earth. Many neutron stars rotate rapidly and have strong magnetic fields, shooting out beams of radiation from their poles. As a neutron star spins, its beams sweep through space. If one of those beams periodically points toward us, we see a pulse of light or radio waves. Such rotating neutron stars are observed as pulsars, cosmic lighthouses flashing on and off with astonishing regularity. If the original star was even more massive, perhaps over 20 times the Sun's mass, then not even a neutron star can withstand the gravitational collapse. The core continues to shrink beyond any known limit and becomes a black hole. In a black hole, gravity is so extreme that nothing can escape, not even light. An invisible boundary called the event horizon surrounds the black hole. Once anything, matter or light, passes inside, it cannot come back out. All the remaining mass of the star is crushed into an infinitely dense point at the center, a singularity hidden behind the event horizon. To an outside observer, what's left is essentially a patch of pure gravity with no light, a true dark star. For a long time, black holes were purely theoretical objects, but now we have compelling evidence that they exist. Astronomers have observed stars orbiting an invisible yet massive object, like planets orbiting an unseen sun, revealing a black hole's presence. One such is at the center of our Milky Way galaxy. We've even imaged the silhouette of a black hole by capturing the glow of superheated gas swirling around its event horizon. These discoveries confirm that these cosmic abysses are real. And indeed, it appears that nearly every large galaxy, including our own, harbours a supermassive black hole at its core. In the aftermath of a star's death, we find the seeds of new beginnings. The material cast off into space, whether the gentle envelope of a planetary nebula or the debris of a supernova, enriches the galaxy with heavy elements. These gases and dust carry the ingredients that will one day form new stars and new planets. Every generation of stars enriches the universe's supply of elements a bit more. The carbon that will course through the veins of future living creatures, the silicon that will build future rocky worlds, the iron that will run in their blood. All were brewed in stars and spread through space by stellar death. In this grand cycle, stars are born from the remains of previous stars. We truly are children of the stars, made from the ashes of ancient suns. When we gaze up at the night sky, we are looking at stars in all phases of their existence. In one patch of sky, a faint nebula may hide infant stars just beginning to shine. Not far away, a bright point might be a mature star, like our sun, steadily burning. Elsewhere, a ruby-red dot could be a bloated red giant approaching its final days. We see brilliant blue supergiants and faint white dwarfs, stellar life in its vibrant youth and its quiet old age. Through science, we have learned to read this stellar panorama like a story. Each star in the sky has a past and a future, a story written in light across cosmic time. And among all those stars, one in particular means the most to us: the Sun. Our Sun is a middle-aged star, quietly burning hydrogen in its core, just as billions of other stars do. But to Earth, this ordinary star is everything. One day, far in the future, the Sun will swell and change as other stars do, eventually shedding its own nebula and becoming a white dwarf. But right now, in the present, the Sun stands at the center of our solar system, warming our world and providing the light that sustains life. Having explored the life cycles of stars in general, we now turn to this one special star, our star, the Sun, to appreciate its life-giving brilliance and its role in our cosmic story. Our journey through the stars now comes home to the one star that matters most to us, the Sun. In the daytime sky, its brilliance overwhelms all other stars, and its warmth makes life on Earth possible. We sometimes forget that this familiar Sun is actually a star at all, a rather ordinary star by cosmic standards, yet utterly extraordinary to us. It's a giant sphere of hot plasma, about 1.4 million kilometers across, and it has been shining for over 4.5 billion years. Every sunrise is a reminder that we live in the glow of a true cosmic powerhouse. The Sun's brilliance is born deep within its core. There, at roughly 15 million degrees Celsius, the Sun fuses hydrogen into helium, releasing a tremendous amount of energy that eventually reaches us as sunlight. In essence, the Sun is a massive nuclear furnace, converting mass into energy via fusion every second. The numbers are staggering. On the order of 600 million tons of hydrogen are fused into helium in the Sun's core each second. This reaction unleashes an immense flood of energy, around 4 by 10, 26 watts, an almost unfathomable figure, which slowly works its way outward. Once it escapes the Sun as light, that energy crosses the 150 million kilometers to Earth in just over 8 minutes. The sunlight that warms your face on a clear morning began its journey in the Sun's core before human civilization even existed. Inside the Sun, the journey of energy begins in the core and moves outward through successive layers. Immediately surrounding the core is the radiative zone, where energy travels outward as photons randomly scattering and gradually diffusing through dense solar plasma. Above that lies the convective zone, where the gas is cooler and more opaque, so heat is carried to the surface by giant boiling motions. Hot plasma rises, cools, and sinks in a rolling, turbulent pattern, rather like a pot of soup simmering on the stove. The visible surface of the Sun, which we call the photosphere, is about 5,500 degrees and appears to us as a dazzling, uniformly bright disk. Up close, it's anything but uniform. It's mottled with a grainy texture, granulation, caused by those convective cells, each one a mass of hot gas the size of Texas, or larger, rising and falling in a rhythmic dance that repeats every few minutes. Our smooth-looking Sun is in fact perpetually roiling and bubbling. The Sun is not a static ball of fire, but a dynamic, magnetic star. Dark spots often freckle its face. Sunspots, cooler regions, though still thousands of degrees hot, where intense magnetic fields suppress the bubbling convection. A single sunspot can be larger than the Earth. Sunspots tend to appear in groups and follow an approximately 11-year cycle. For several years, the Sun shows many spots and heightened activity, the solar maximum. Then it calms down to a nearly spotless state, solar minimum, before the cycle begins anew. Along with sunspots, the Sun sometimes unleashes colossal eruptions. Solar flares flash brightly, and even more violent coronal mass ejections can hurl billions of tons of charged plasma into space. If that plasma happens to intersect Earth, it can interact with our planet's magnetic field and upper atmosphere, causing geomagnetic storms. One lovely side effect of these storms is the aurora, the northern and southern lights. Delicate curtains of green and red light dance in polar skies when energetic particles from the sun excite the atmosphere. It's awe-inspiring to realize that shimmering auroras on Earth are a direct result of storms on the sun, 150 million kilometers away. On rare occasions, the moon passes directly in front of the sun, perfectly blocking its bright disk. Day turns to an eerie twilight as the sky darkens and the temperature drops. Stars come out in the daytime sky. This is a total solar eclipse. Only the sun's ghostly corona becomes visible, surrounding the black silhouette of the moon, pale filaments of the sun's outer atmosphere, normally hidden by its brilliance. For a few minutes, observers can gaze at the sun's delicate crown, a sight few ever forget. Ancient peoples often regarded eclipses as powerful omens. Today, we understand the celestial geometry behind the event, yet the experience still overwhelms us. In those moments, we are reminded that even our brilliant sun can be momentarily overshadowed by cosmic chance. The sun's influence extends far beyond the orbit of the outer planets. A constant stream of charged particles, known as the solar wind, flows outward from the sun in all directions, bathing the entire solar system. This solar wind creates a vast protective bubble around our solar system called the heliosphere. Within the heliosphere, the sun's magnetic field and outflowing particles help deflect many high-energy cosmic rays coming from interstellar space. In essence, the sun's presence carves out a little haven in the galaxy, a region dominated by our star's influence. The Voyager spacecraft, which have traveled to the edge of the solar system, detected the boundary of this heliosphere many billions of kilometers away, where the solar wind finally slows and mingles with the interstellar medium. Our sun's reach, though invisible, is immense. For Earth, the sun is the giver of light and heat, the fundamental energy source for almost everything that happens. Every beam of sunlight nourishes our planet. Plants use sunlight to drive photosynthesis, creating the food and oxygen that animals, including us, depend on. Sunlight drives the evaporation of water from oceans, lakes, and soil, lifting moisture to form clouds. Later that water falls as rain or snow, filling rivers and aquifers. The sun powers the winds and weather patterns as well. Sunlight heats some parts of Earth more than others, generating atmospheric currents and ocean convection that moderate climate and distribute rainfall. Even fossil fuels are essentially ancient sunshine stored by plants and plankton millions of years ago. Virtually every calorie of energy that our civilization consumes can be traced back to the sun's rays. In a very literal sense, the sun is the engine of life on Earth. Throughout human history, people have revered the sun. Many ancient cultures worshipped it as a deity or personified it as a powerful life-giver. The ancient Egyptians honored Ra, the sun god who sailed the sky by day. The Inca of Peru built temples to Inti, their sun god, and held festivals to celebrate the sun at solstices. In Hindu tradition, the sun is venerated as Surya, dispeller of darkness and healer of illness. Sun symbols and myths appear in cultures worldwide, a testament to the star's importance in human life. It's easy to see why. The sun's daily rising brought warmth, light, and growth. Its setting brought darkness, cold, and uncertainty. In the sky's grand theatre, The sun was the benevolent force that made crops grow and kept the cold at bay, so it naturally earned a place of highest respect in human societies. Despite its crucial role for us, the sun is but one ordinary star among countless others. In the scheme of our galaxy, it's of medium size and brightness. Many stars out there are far larger and more luminous, supergiants that would dwarf our sun, while many more are smaller, dimmer red dwarfs that barely outshine embers. If the sun were placed in a distant part of the Milky Way, it might not stand out at all. And yet, to us, it is uniquely precious. Our sun is also somewhat unusual in being alone. Many stars its age have companions in binary systems. The sun's solo nature may have been a boon for life. A close companion star could have disrupted the stable orbits of planets, or bathed Earth in harmful radiation. In the quiet of space, our sun spends its days as an unremarkable yellow dwarf star. But here on Earth, it is the center of everything. The sun is about 4.6 billion years old, roughly middle-aged for a star of its type. By studying other stars and the traces of our early solar system, scientists have pieced together the sun's origin and eventual fate. Our sun was born from the collapse of a cloud of gas and dust in our region of the Milky Way. As that protostellar cloud contracted under gravity, a spinning disk of material formed around the nascent sun. From that disk, the planets, moons, and other bodies of our solar system eventually coalesced. Ever since ignition, the sun has been in a stable middle age, quietly converting hydrogen to helium in its core. It's expected to remain in this stable phase for about another 5 billion years. But nothing in the cosmos lasts forever. And one day, the sun's gentle warmth will turn fierce. In about 5 billion years, the sun's core will run low on hydrogen fuel. When that happens, the sun's life story will enter its dramatic final chapters. The core will contract and heat up as fusion slows, and the outer layers of the sun will swell enormously. Our sun will become a red giant. Its diameter will expand many times over, likely reaching past the orbit of Mercury and Venus, perhaps even enveloping the Earth. If Earth is engulfed, it will be vaporized in the sun's hot plasma. But even if our planet somehow survives just outside the sun's bloated atmosphere, the intense heat would boil away Earth's oceans and atmosphere, leaving it a charred, lifeless rock. Eventually, the sun will cast off its outer layers, creating a glowing planetary nebula that will spread into surrounding space. The core of the sun, now out of nuclear fuel, will be left behind as a dense, hot white dwarf no larger than the Earth. For a time, that white dwarf will illuminate the departing nebula with an eerie glow. The gorgeous colours of our sun's last planetary nebula might be visible for tens of thousands of years. After that, the nebula will dissipate into the stars, and the white dwarf will cool over billions of years, fading to a black dwarf. Thus, our sun's tail will come to an end. From diffuse cloud to shining star to gentle ember, and finally to darkness. Long before those final stages, however, life on Earth will have been profoundly affected. As the sun very slowly ages, it is actually getting brighter. In a few 100 million years, the sun's increased radiation may heat Earth enough to trigger drastic climate changes, potentially a runaway greenhouse effect that could sterilize the planet's surface well before the sun becomes a red giant. It's sobering to realize that the habitable conditions we enjoy are temporary on geological timescales. Fortunately, these changes occur on scales of time almost inconceivable to the human mind. We're talking hundreds of millions to billions of years in the future, time enough perhaps for our distant descendants, if any, to seek refuge elsewhere in the cosmos. Still, contemplating the sun's full life cycle drives home a poignant truth. Even the life-giving stars must eventually age and die, and nothing in the physical universe lasts forever. For now, our sun is a steady beacon in the sky, rising and setting with reassuring regularity. It will continue to shine warmly for many millions of generations to come, a comforting constant in a changing world. Earth sits at just the right distance from the sun, in what's often called the Goldilocks zone, where temperatures allow liquid water and life as we know it. This fortunate position, combined with the sun's stable output, has allowed life to thrive on our planet. Every living thing, from the simplest microbe to the tallest tree, is sustained by the sun's energy. We live bathed in sunlight, and even at night, reflected sunlight from the moon softly illuminates our world. The sun's regular cycle of day and night has set the rhythm of life's activities for eons. Each sunrise and sunset binds us to the ancient humans who once stood under these skies. We greet the dawn as they did, feeling the sun's warmth on our skin. We watch the sunset with a mix of gratitude and hope, trusting that the sun will rise again. The sun's daily journey across the sky has inspired myths of solar chariots and sun gods, and its dependable return each morning has been a source of comfort through the ages. In the cool twilight that follows sunset, we might reflect on how tomorrow the sun will climb again above the horizon, bringing light and renewing life's promise, just as it has every day of our lives and our ancestors' lives, stretching back through time. When we cautiously observe the sun through a filtered lens, never with unprotected eyes, we're essentially looking at a typical star up close. Its surface seethes and occasionally flares, but to us, it mostly appears calm and golden. If we were on a planet orbiting another star, our sun would be just one more point of light in the starry sky, perhaps part of someone else's constellation. It's humbling to imagine that from a distant vantage, our sun is nothing special. Yet here, at home, it is uniquely beloved. That dual perspective, the sun as an ordinary star and the sun as our nurturing luminary, reminds us of our place in the universe. We orbit an unremarkable star in a galaxy of billions, but that star means everything to us. The sun's gravity holds the entire solar system together. It is the anchor of our cosmic neighborhood. Earth and 7 other planets dutifully orbit the sun, along with a myriad of dwarf planets, moons, and countless smaller bodies like asteroids and comets. Year after year, the planets trace the same paths around their stellar parent, bound by its gravitational embrace. Without the sun's mass drawing us in, Earth would wander off into the void. The gentle pull of the sun's gravity keeps us at just the right distance, on a trajectory that has allowed life to persist. Our day length, our year length, our tides and seasons, all are ultimately governed by the sun's influence. Standing under the noonday sun, it's easy to take its light for granted. But with understanding, that light becomes something profoundly magical. Energy released in the sun's core eons ago, traversing space to sustain life on a small blue world. The sun connects us to the wider universe. The very atoms in our bodies were forged in long dead stars. And now, a living star pours energy upon us to fuel our existence. We are, in a real sense, children of the stars, and our particular parent star is the sun. As we come to the end of this part of our cosmic journey, we reflect on our sun's story. In galactic terms, it's an unassuming middle-aged star. But for us, it is an irreplaceable source of life and light. Day after day, the sun's steady shine allows forests to grow, winds to blow, and oceans to teem with life. Its gravity keeps Earth securely in orbit. Its light defines our days. The sun will not shine forever, but for countless ages to come, it will continue to rise on our descendants and bestow its warmth. Orbiting this life-giving star is a family of planets, our neighbours in space, each with its own character and mysteries. Having honoured and understood our sun, we are ready to venture farther out. In the next chapter of our journey, we will leave our star's surface and step out into the realm of those planets, exploring the diverse worlds that share our solar system under the sun's watchful light. The story continues as we travel from our star to the worlds that orbit it on our ongoing voyage through the cosmos. In a quiet arm of the Milky Way galaxy, countless stars are born from vast clouds of gas and dust. Over 4.5 billion years ago, one such cloud began to collapse under its own gravity. At first it was cold and dark, drifting silently in space, but gradually it started to spin and flatten into a broad disk. Perhaps a shock wave from a nearby supernova explosion triggered this collapse, setting our solar system's creation in motion. Matter drew toward the center, compressing tighter and tighter, heating up from the pressure. In that dense heart, a new star was forming, destined to become our sun. As the protostar at the center grew hot and bright, the surrounding disk of gas and dust spun around it like a whirlpool. Within that disk, tiny dust grains gently collided and stuck together. Slowly, over countless millennia, grains became pebbles, pebbles became boulders, and boulders became larger bodies. These were the seeds of planets. Closer to the nascent sun, the heat was intense, vaporizing ice and driving away most gases, so only rock and metal could clump together. In these inner regions, the small solid planets were born. Farther out, beyond a certain distance, it was cold enough for ices and gases to remain. In these outer regions, much larger planets formed, accumulating not just rock, but abundant ice, and the light gases like hydrogen and helium. While the young sun continued to contract and brighten, the planets took shape around it. The early solar system was a chaotic place. Protoplanets and moon-sized bodies frequently collided. Each impact sent shockwaves through the growing worlds, melting and merging them. Some collisions were gentle, others catastrophic, shattering worlds and reassembling them. Over time, most of the debris either merged into the planets or was ejected from the system. Eventually, 8 major planets emerged, circling the sun in nearly circular orbits, each in its own band of distance. In the first few 100 million years, impacts were frequent, the period known as the Late Heavy Bombardment, pockmarking surfaces with craters we can still observe today on worlds like the Moon and Mercury. But gradually, as the planets cleared their paths, the chaos abated. When finally the sun ignited into a stable star, it unleashed a stream of charged particles, a solar wind that rushed outward and blew away the remaining nebula gas. The stage was set for the long, slow evolution of these planets and everything on them. Our sun was likely born in a cluster alongside many other newborn stars, all emerging from the same cloud. But over time, these stellar siblings drifted apart across the galaxy. The ingredients that formed the planets, and even our own bodies, were forged in older stars and supernovas long before our sun existed. Truly, we are made of stardust. The journey of our solar system had begun, and we begin our voyage through it with the small rocky worlds closest to the sun. Blazing close to the sun, the first planet Mercury races around our star. Mercury is a small, rocky globe, indeed the smallest of the 8 planets. It is only slightly larger than Earth's moon, and much like the moon, its surface is heavily cratered and ancient. Travelling around the sun in just 88 Earth days, Mercury lives in a world of extremes. Daytime on Mercury lasts for months, and under the unfiltered sunlight the surface becomes scorching hot, hotter than an oven, hot enough to melt lead. But Mercury has virtually no atmosphere to hold the heat. So when night finally comes, lasting another long 2 months, the temperature plummets into deep cold. The ground that was glowing with heat in the day becomes frigid and still by night. In Mercury's polar regions, there are craters so deep and so permanently shadowed that the sun's rays never reach their floors. In those eternal darknesses, it is cold enough that water ice can persist. Indeed, deposits of ice lie hidden in the polar craters, a surprising reservoir of frost on this sun-scorched little world. Mercury rotates slowly, so slowly that it only spins 3 times on its axis for every 2 orbits it makes around the sun. A single day-night cycle on Mercury, from one sunrise to the next, actually takes about 176 Earth days, which is even longer than Mercury's own year. This unusual spin-orbit dance means time behaves strangely on Mercury. An observer standing on Mercury's surface would see an odd spectacle. At some longitudes, the sun might rise, then pause, and briefly dip below the horizon before rising again to continue its journey across the black sky. The sky itself would be jet black even at noon, since there is no significant atmosphere to scatter the sunlight into a blue glow. The sun would appear more than 3 times larger than it does from Earth, and far more intense. All around, the landscape would be grey and silent, broken by countless craters and sharp-edged cliffs where the crust has buckled. It is a desolate, quiet landscape, enduring some of the most extreme conditions in the solar system. Mercury is not easily seen from Earth's perspective. Always hanging close to the sun, it often gets lost in the solar glare. Only during certain twilights does Mercury peek out, visible as a tiny point of light low on the horizon, moving swiftly against the backdrop of dawn or dusk. Fittingly, the ancient Romans named it after Mercury, the fleet-footed messenger of the gods. It's the fastest planet, and the name suits its quick, elusive presence in our sky. In the vacuum surrounding Mercury, there is almost no air, just a thin scattering of atoms blasted off its surface by the sun's radiation. Without a substantial atmosphere, and with such wild swings between day and night, Mercury's surface features remain frozen in time. A crater made by an impact billions of years ago still looks fresh, as there is no wind or water to wear it away. Change comes very slowly to this tiny world. Despite its small size, Mercury has a disproportionately large iron core that generates a weak magnetic field, an unexpected trait for such a tiny planet. Drifting outward from Mercury's orbit, we next encounter Venus, the second planet from the Sun. Venus is nearly the same size as Earth, often called Earth's sister planet in terms of diameter and mass. But in almost every other respect, Venus is an ominous opposite to Earth. It is a world cloaked in thick, reflective clouds and suffocated by a massive atmosphere. While our Earth is mild and bursting with life, Venus has become a sweltering hothouse where life as we know it could not survive. Approaching Venus, one first sees a brilliant white orb hanging in space. Its thick layer of clouds covers the entire planet, making Venus gleam like a pearl. Those clouds are not made of water vapor as on Earth, but of corrosive sulfuric acid droplets. Below the clouds, the atmosphere is composed primarily of carbon dioxide. This dense blanket of CO2 traps the sun's heat with ruthless efficiency. Sunlight passes through to warm the surface, but the heat cannot escape back into space. This trapped heat has driven Venus into a runaway greenhouse effect. As a result, Venus's surface temperature is hotter than that of Mercury, even though Venus is nearly twice as far from the Sun as Mercury. On the ground, temperatures on Venus soar to around 465 degrees, 869 degrees. The air is stiflingly dense. The atmospheric pressure at the surface is about 90 times that of Earth's, akin to being almost a kilometre beneath the ocean. The landscape is lit by a perpetual deep orange twilight, because the thick clouds permit only a dim, filtered light to reach the ground. If one could stand on Venus's rocky surface, one would see hazy outlines of terrain under a smoggy orange sky. The ground is dry and littered with broken rocks. No liquid water flows on Venus. Any oceans it may have had in the distant past have long since boiled away. The heat is unrelenting, the air filled with choking carbon dioxide, and the pressure immense. A human standing there without protection would not survive more than a few moments. Even our hardy robotic probes have survived only an hour or two on Venus's surface before being overcome by the extreme conditions. Despite these infernal conditions, Venus remains a fascinating and mysterious world to scientists. Its surface appears relatively young, geologically speaking, indicating that some process has renewed large portions of the planet in the last 500 million years. The planet is covered in volcanoes, more volcanoes than any other planet in the solar system, though none are known to be erupting currently. It's possible that Venus undergoes periodic resurfacing events, colossal volcanic outpourings that repave entire regions. This would explain why Venus has few impact craters. The old craters may have been buried under lava flows, leaving the surface looking smoother and younger than it actually is. In a sense, Venus may erase parts of its past from time to time, hiding its history beneath fresh rock. High above Venus's surface, fierce winds circle the planet. In the upper atmosphere, winds race around at hundreds of kilometers an hour, carrying the clouds completely around Venus in just a few Earth days. This phenomenon is called superrotation. The atmosphere spins around much faster than the planet itself turns. Closer to the surface, the air is so thick and sluggish that any breeze is minimal. One might feel only a slow, gentle stirring despite the hellish environment. Venus also rotates in the opposite direction of most planets. On Venus, the sun rises in the west and sets in the east. Moreover, Venus rotates very slowly. A single rotation takes 243 Earth days. In fact, a day on Venus, one full spin, is actually longer than a Venusian year, 225 Earth days. These oddities make Venus a truly alien world in terms of time and motion. From space, however, Venus appears deceptively serene and beautiful. Its blanket of golden white clouds gives it a smooth, unblemished face. Only by using radar to peer through the clouds, or by sending probes into its atmosphere, do we discern the tortured landscape hidden below. As we now leave Venus behind in our journey, the brilliant planet fades into the darkness. In Earth's sky, Venus's brilliance earned it the title of the morning star or evening star, depending on when it appears. And ahead, the pale blue glow of Earth comes into view. Our home, waiting to be explored next. Our voyage now brings us to the third planet from the Sun, Earth. At about 150 million kilometers from the Sun, Earth sits comfortably within the zone where water can exist as liquid. This fortunate position, along with Earth's size and composition, has made it a haven for oceans, atmosphere, and life. Seen from space, Earth shines as a vibrant blue marble set against the blackness of the cosmos. Swirls of white clouds dance above blue oceans and brown-green lands. Polar caps of white ice cap the planet at top and bottom. In all the vast darkness of space that we've travelled through so far, Earth stands out as a lively, welcoming oasis. Earth's atmosphere is a delicate blanket of gases encircling the planet. It is mostly nitrogen and oxygen, the latter produced and maintained by the abundance of plants and algae. This thin veil of air scatters the sun's light to create blue skies by day and offers protection from harmful solar radiation. Beneath it, water covers more than 2/3 of Earth's surface in interconnected oceans. These oceans regulate the planet's climate and nurture an incredible diversity of life. Continents with mountains, forests, and deserts drift slowly on tectonic plates over Earth's molten mantle, their shapes ever so gradually changing over millions of years. Rain falls from clouds, rivers run to the seas, and life flourishes almost everywhere. From the deepest ocean trenches to the highest mountain peaks, and from equatorial jungles to polar ice fields. Unlike the barren worlds we've seen so far, Earth is alive in many senses of the word. It has active geology and active biology. Volcanoes occasionally erupt, forming new land. Earthquakes remind us that the planet's crust is mobile and dynamic. The atmosphere and oceans circulate constantly, driving weather and climate. And of course, the biosphere, the global sum of all ecosystems, transforms the surface and the air. Green forests and phytoplankton enrich the air with oxygen. Countless living creatures, big and small, interact in a web of life. Over billions of years, life has arisen and evolved on Earth, from simple microbes that began altering the atmosphere, to complex creatures that now gaze back at the cosmos. All the while, Earth's position and stability have allowed water to persist in liquid form, nurturing this delicate continuum of life. Earth is our home, and so far, the only place in the universe known to harbour life. In the darkness of space, it is a jewel brimming with activity and colour. Earth rotates once every 24 hours, giving us the cycle of day and night that all life has come to anticipate. The gentle rhythm of sunrise and sunset has occurred unbroken for billions of years. Meanwhile, Earth orbits the Sun once every year, and the planet is tilted on its axis by about 23.5 degrees. This tilt causes the seasons. As Earth travels around the Sun, each hemisphere tilts toward or away from the Sun at different times, bringing the warmth of summer or the cold of winter. These cyclical changes, day and night, summer and winter, set the stage for the countless natural cycles that life has synchronized with. They are the heartbeat and breathing of our planetary environment, steady and reliable over the ages. High above the atmosphere, curtains of aurora borealis and aurora australis shimmer at the poles as Earth's magnetic field directs charged solar particles into the upper air, a gentle light show that paints the night in glowing green and red. Travelling with Earth on its yearly journey around the Sun is our moon, Earth's constant companion. The moon is Earth's only natural satellite, a silent grey world that has orbited our planet for over 4 billion years. It formed in the aftermath of a colossal impact early in Earth's history, when a Mars-sized body collided with the young Earth. The debris from that cataclysm eventually coalesced into the moon, which slowly receded to the distance at which we see it today, about 384,000 kilometers away. Ever since, the Moon has been locked in orbit around Earth, completing a circuit roughly every 27 days. The Moon is airless, waterless, at least on its surface, and starkly beautiful in its austerity. Its diameter is about a quarter of Earth's, making it proportionally one of the largest moons relative to its planet in the solar system. The Moon's gravity is only 1/6 as strong as Earth's. Its surface is covered in fine dust and rocks, pitted by innumerable craters from meteor impacts. You can see light and dark patches on the Moon with the naked eye from Earth. The dark areas are vast plains of solidified lava, called maria, from ancient volcanic activity, while the brighter areas are highlands, heavily peppered with craters. Like Mercury, the Moon experiences extreme temperature swings between day and night, since there is no atmosphere to retain heat. Daytime on the Moon is blazingly bright and can be quite hot, while lunar night is bitterly cold. Both day and night each last about 2 weeks, because the Moon rotates slowly. One side of the Moon perpetually faces Earth, while the opposite side, the far side, remains hidden from direct view. This is because the Moon is tidally locked with Earth, rotating on its axis in the same time it takes to orbit once around Earth. As a result, for any given spot on the Moon, the Sun rises roughly once every 4 weeks, and Earth itself hangs fixed in the lunar sky for observers on the Moon's near side, or is never seen at all from the far side. On the Moon's near side, if you were standing on the grey, dusty surface, you would see Earth in the sky, much larger and brighter than the Moon appears to us, going through phases just as the Moon does when viewed from Earth. Earth would not rise or set from that vantage point, but instead would hover in nearly the same place in the sky, slowly cycling through its full globe, half globe, and crescent phases as sunlight falls on it from different angles. The Moon's presence has a profound effect on Earth. Its gravity tugs at our oceans, causing the regular rise and fall of tides. By stabilizing the tilt of Earth's axis over long time scales, the Moon has helped maintain a relatively stable climate, preventing wild swings that might have been detrimental to the development of life. The Moon's pale light at night, actually reflected sunlight, has guided nocturnal creatures and inspired humans for as long as we have existed. And yet, the Moon itself is a dead world. There is no air to carry sound, no flowing water, no life that we know of. It is the epitome of silence and stillness. A footprint left on the Moon's surface could remain there for millions of years, untouched by wind or rain. Despite its lifelessness, the Moon is intimately connected to Earth's story. It likely played a role in making Earth the hospitable world it is. In turn, Earth's gravity has moulded the Moon's fate, synchronizing its rotation and pulling it ever so slightly farther away with each passing eon. As our nearest celestial neighbour, the Moon was the first, and so far only other world visited by humans, who left bootprints and flags in the lunar dust as testament to our desire to explore. Those marks too remain, preserved in the Moon's undisturbed terrain. Standing on the Moon and gazing back at Earth, one would see our blue planet glowing with life against the black, cosmic backdrop. This perspective underscores how special Earth truly is. Now, as we turn our gaze outward again, we leave behind the Earth-Moon system. The Sun's light dims a little more with distance, and the red planet Mars awaits as the next step on our journey through the solar system. Mars is the next planet out from Earth, orbiting roughly 1.5 times farther from the Sun than we do. It is a small, cold, desert world, often called the Red Planet, because of its distinctive rusty colour. Mars is about half the size of Earth in diameter and only about 1/10 of Earth's mass. Its gravity is weaker, around 38% of Earth's gravity, so a person would feel much lighter there. The red hue that tints the entire planet comes from iron-rich dust that covers its surface, effectively rusting in the thin air and giving Mars its ruddy complexion when seen from afar. The Martian landscape is both familiar and alien. It has mountains, valleys, and vast plains, but all is dry and quiet. Mars has the largest volcano in the solar system, Olympus Mons, a gigantic shield volcano that towers about 22 kilometers high, nearly 3 times the height of Mount Everest. This volcano is so broad at its base that it would cover an area the size of Arizona. Though immense, Olympus Mons is long extinct, having last erupted millions of years ago. Near the Martian equator stretches a colossal canyon system called Valles Marineris. This network of canyons runs for about 4,000 kilometers, nearly 1/5 the circumference of Mars. In places, it is up to 7 kilometers deep. If it were on Earth, it would span the width of the United States. Standing at the edge of Valles Marineris, you would gaze out into a chasm so vast that it disappears into the horizon. Mars is far colder and drier than Earth today. Its atmosphere is extremely thin, less than 1% the density of Earth's air, and made mostly of carbon dioxide. Because the air is so thin, it holds very little heat. Even though Martian midday at the equator in summer might feel mildly warm, the warmth vanishes as soon as the sun sets. On a summer day, the temperature might rise to about 20 degrees, 68 degrees in the sun, but at night it can plunge to 90 degrees, 130 degrees. Near the poles, or in winter, temperatures stay well below freezing all the time. The sky on Mars is typically a butterscotch colour due to fine dust suspended in the air. At sunrise and sunset, the sky can turn a cool blue around the sun, a reversal of Earth's red-orange dawns and dusks. Wispy clouds sometimes form high above, made of ice crystals, but they are relatively sparse. Evidence suggests that Mars was not always such a barren, frozen world. Long ago, Mars had flowing liquid water on its surface. Ancient river channels and delta-like formations are etched into the terrain, and rovers have found rocks and minerals that only form in the presence of water. There are large sheets of water ice buried under the rocky soil in many places, especially near the poles and inside craters. Mars even has polar ice caps that grow and recede with the seasons. In winter, a cap of carbon dioxide frost, dry ice, covers each pole, and in summer, some of that sublimates away to reveal layers of underlying water ice. These caps and the patterns in Martian soil tell a story of climate cycles and a past that may have been more hospitable. One can imagine ancient Martian lakes or rivers rippling under a pink sky eons ago, though today such scenes have vanished. Today, Mars is a quiet world, with only the whisper of the wind to disturb it. That wind can sometimes stir up the ubiquitous dust into vast storms. On occasion, Mars experiences planet-wide dust storms that can enshroud the entire globe in a red haze for weeks at a time. These storms often begin as smaller dust devils and whirlwinds on the surface, which then grow and merge into larger tempests. When the dust settles, it leaves dunes and drifts that slowly shift over time. Apart from the wind, Mars is largely still. There is no rain, only thin frost that can form on winter mornings and then evaporate by midday. The silence on Mars is profound. No sound of running water, no rustling of leaves, only perhaps the faint murmur of a cold breeze. Mars has two tiny moons of its own, Phobos and Deimos. Unlike our large spherical moon, these Martian moons are small and irregularly shaped, looking more like captured asteroids than typical moons. Phobos, the larger of the two, is still only about 22 kilometers across, and Deimos is around 12 kilometers across. They orbit very close to Mars. Phobos whips around the planet in just 7 hours, faster than Mars rotates, causing it to rise in the west and set in the east on the Martian sky, twice each Martian day. The surfaces of these moons are dark, cratered, and covered in dust. Over extremely long periods, Mars's gravity is pulling Phobos inward. Tens of millions of years from now, Phobos may spiral so close that it breaks apart, possibly forming a faint ring around Mars, before the debris ultimately falls onto the planet. For now, Phobos and Deimos persist as quiet companions, casting tiny moving shadows on the rust-coloured ground as they pass overhead. In humanity's imagination, Mars has always held a special place. It is the most Earth-like of the other planets in certain ways. Martian days are just about 24.6 hours long, very close to our own, and its axis tilt gives it seasons akin to Earth's, though more extreme. Because of these similarities and its relative closeness, Mars has long been the focus of hopes that it might harbour life, or that humans might someday walk its deserts. So far, no evidence of life has been found on Mars. Today, several robotic explorers, rovers like Curiosity and Perseverance, traverse the Martian terrain, their tire tracks the only sign of activity. They drill into rocks and analyze soil, patiently gathering clues about Mars's past habitability in the silent, empty landscapes. The exploration continues with rovers and landers probing its soil and atmosphere. They operate in the lonely Martian silence, studying the rocks and dust, and occasionally recording the soft whisper of the Martian wind. Sunsets on Mars are oddly hued. As dusk falls, the sky around the setting sun turns a cool blue, a reversal of Earth's fiery red sunsets. At night, the two small moons, Phobos and Deimos, scuttle across the sky, and if you knew where to look, you could even see Earth itself as a bright bluish star on the Martian horizon. Stepping away from Mars, we prepare to venture beyond the realm of the inner rocky planets. Past Mars's orbit lies a wide expanse filled with countless asteroids, the remnants of primordial building blocks that never coalesced into a planet. Beyond that asteroid belt, the solar system transforms dramatically. Farther out, a giant world of gas and clouds awaits. Mars fades behind us as we approach the massive domain of Jupiter, king of the planets. Beyond the orbit of Mars and the asteroid belt lies Jupiter, the fifth planet from the Sun, and by far the largest. Jupiter is a true giant, more massive than all the other planets combined. In fact, if it had been about 80 times more massive, it could have ignited into a small star. Instead, it became a gas giant, a colossal sphere of hydrogen and helium gas with no solid surface. Jupiter's presence dominates its region of space. It earned its name from Jupiter, king of the ancient Roman gods, and rightly so. Orbiting about 778 million kilometers from the Sun, 5.2 astronomical units, Jupiter takes almost 12 Earth years to complete one circuit. From that distance, the Sun's light is much dimmer than we're used to, but Jupiter itself shines brightly in our night skies, outshone only by the Moon and Venus, and occasionally Mars. The planet acts like a gravitational anchor in the solar system. Its immense pull shapes the orbits of countless asteroids and comets. At times, it has likely diverted dangerous comets away from the inner solar system, earning a reputation as a potential shield for Earth. Approaching Jupiter, one cannot miss its magnificent appearance. The planet is striped with bands of white, yellow, tan, and reddish-brown, swirling in constant motion. These bands are fast-moving cloud belts in Jupiter's upper atmosphere, arranged in alternating east-west jet streams. The lighter bands, called zones, and the darker bands, called belts, encircle the globe. They are composed of ammonia crystals and other compounds forming clouds at different heights. The boundaries between these bands are turbulent, spawning enormous storms. The most famous storm on Jupiter is the Great Red Spot, a vast oval-shaped hurricane-like system big enough to swallow Earth whole. This gigantic storm has raged for centuries, at least since the 1600s, when astronomers first noted a red spot on Jupiter through early telescopes. It rotates counterclockwise and takes about 6 Earth days to spin around once. Lately, it has been observed to be gradually shrinking, but it remains an iconic feature of Jupiter's restless atmosphere. Jupiter's weather is intense and exotic. The planet spins extremely fast, completing a rotation in just under 10 hours despite its huge size. This rapid spin causes Jupiter to bulge at the equator and flatten at the poles slightly. It also drives violent winds. At the edges of the colored bands, wind speeds can reach over 300 kilometers per hour. Ammonia ice clouds cast shadows on deeper layers of the atmosphere, and lightning has been detected in the cloud belts, indicating thunderstorms on a colossal scale. If one could descend into Jupiter, the atmosphere would grow denser and hotter, transitioning from gas to a kind of hot, thick soup of fluids. Ultimately, deep below, the pressures become so extreme that hydrogen gas is compressed into a strange liquid metallic form. In this hidden interior, Jupiter likely has a diffuse core of heavier elements, but it's not a solid surface one could land on. Jupiter still emits more energy than it receives from the Sun, as it slowly releases heat from its formation, a hint that this giant planet is still cooling and contracting ever so slightly. Jupiter is also a world of auroras and magnetic might. It has an enormously strong magnetic field, thousands of times stronger than Earth's. This magnetic field traps charged particles and funnels them toward Jupiter's poles, creating auroras far larger and more powerful than Earth's northern and southern lights. These auroras shine in ultraviolet and infrared wavelengths, invisible to human eyes, but observable by instruments. They are a sign of Jupiter's dynamic electromagnetic environment. The magnetic field is generated by the motion of that metallic hydrogen deep inside Jupiter's interior, acting like a cosmic dynamo. It also means that the space around Jupiter is filled with intense radiation, making the environment hazardous for spacecraft and would-be explorers. Encircling Jupiter is a retinue of moons, a miniature solar system in itself. Jupiter has nearly 100 moons known so far, with 4 large moons that stand out. These 4, Io, Europa, Ganymede, and Callisto, were first observed by the astronomer Galileo Galilei in 1610 using one of the earliest telescopes. These 4 moons are known today as the Galilean satellites, and they're some of the most fascinating destinations in our solar system. Galileo's sighting of these moons in 1610 was the first evidence that not all celestial bodies orbit Earth, a landmark discovery in astronomy. Each of these moons is unique, with its own character and mysteries. As Jupiter's immense gravity tugs on them, it influences their geology and even generates internal heat through tidal forces. The closest of the Galilean moons is Io, a world of fire and brimstone. Roughly the size of our moon, Io is the most volcanically active body in the solar system. Its surface is mottled orange, yellow, and white, coloured by sulfur compounds from constant volcanic eruptions. Over 100 active volcanoes have been observed on Io. Some of them blast out sulfur dioxide gas and lava fountains that rise dozens of kilometres high. The intense gravitational pull of Jupiter, along with tugs from the other Galilean moons, flexes Io's interior, heating it through friction and keeping its subsurface partially molten. This makes Io a continually erupting world, its landscape ever renewed by lava flows. Despite its hellish surface, Io has an extremely thin atmosphere, mostly sulfur dioxide, that freezes onto the ground at night. Next is Europa, slightly smaller than our moon, presenting a stark contrast to volcanic Io. Europa is an icy world, its surface a smooth shell of water ice, crisscrossed by long, dark cracks and streaks. The surface is one of the brightest in the solar system, reflecting much of the sunlight. Hardly any craters mar Europa's exterior, indicating that it is young and active, continuously resurfaced by processes below. Scientists are confident that beneath Europa's frozen crust lies a global ocean of liquid water, kept warm by tidal heating from Jupiter's pull. This hidden ocean, possibly in contact with a rocky seabed, makes Europa one of the prime candidates in the search for extraterrestrial life in our solar system. Occasionally, plumes of water vapour have been detected, spewing from Europa's surface cracks, hinting at active geysers linking the ocean below to space above. Europa's enigmatic nature, a frozen surface hiding a deep, dark ocean, captures our imagination and begs further exploration. If one could stand on Europa's frozen surface, Jupiter would loom in its sky, a massive striped orb nearly 14 times the apparent diameter of our moon, as seen from Earth, casting a faint light on the icy plains. Moving outward, we come to Ganymede, the largest moon of Jupiter, and indeed the largest moon in the entire solar system. Ganymede is even bigger than the planet Mercury, though far less massive, being made of ice and rock. It is a world of varied terrain. Some regions are dark and heavily cratered, marking an ancient surface, while other regions are lighter, with grooves and ridges from tectonic activity in the distant past. Ganymede is unique among moons, in that it has its own internally generated magnetic field, a miniature magnetosphere, likely created by a convecting molten iron core. Ganymede is also believed to have a deep subsurface ocean beneath its icy crust, sandwiched between layers of ice. Although it does not show as much surface activity as its neighbour Europa, Ganymede's combination of size and complexity makes it a compelling world in its own right. The fourth Galilean moon is Callisto, the most distant of the big four. Callisto is a heavily cratered, ancient world of ice and rock, appearing much like a frozen memory of the early solar system. Its entire surface is covered in impact scars. In fact, it is one of the most cratered surfaces we know. This suggests that Callisto's exterior has remained largely unchanged for billions of years, with no tectonics or volcanism to resurface it. Beneath its battered crust, Callisto too might harbour a salty ocean, hinted at by magnetic measurements from passing spacecraft. If so, it would mean all three of Jupiter's large icy moons, Europa, Ganymede, and Callisto, contain hidden oceans beneath their crusts. Callisto's inertia in terms of geology, contrasted with the hyperactivity of Io, or the youthful surface of Europa, provides a window into different possible fates of moons around a giant planet. Jupiter's family of moons doesn't end with the Galileans. Dozens of smaller moons orbit further out, ranging from icy spheres a few hundred kilometers wide to tiny captured asteroids only a few kilometers across. They have a variety of orbits, some circling in the same direction as the big moons, others in opposite retrograde paths, likely captured by Jupiter's gravity long after the planet formed. These moons are too small to hold round shapes or atmospheres, but they add to the richness of Jupiter's system. And faintly encircling Jupiter itself is a thin ring system made of dust particles ejected from some of these small moons by meteor impacts. Unlike the broad, bright rings of Saturn, Jupiter's rings are dark and tenuous, visible only when backlit by the sun. As we move away from Jupiter, we reflect on the sheer scale and diversity of this giant planet's domain. From raging storms in multicolored clouds to moons that might hide oceans or erupt with lava, Jupiter offers a microcosm of wonders. Leaving the influence of Jupiter's immense gravity, we set our course outward once more. Ahead of us glows a pale golden point encircled by shining rings. The beautiful planet Saturn awaits. Continuing outward, we arrive at Saturn, the sixth planet from the Sun. Saturn is another gas giant, slightly smaller than Jupiter, but still enormous, about 9 times Earth's diameter and over 95 times Earth's mass. It takes nearly 30 Earth years for Saturn to complete one orbit around the Sun. The sunlight here is only a fraction of what we experience on Earth, casting a gentle, distant glow on the planet. Saturn is famed for the stunning system of rings encircling its equator, a feature unparalleled in beauty and extent. In composition, Saturn is mostly hydrogen and helium like Jupiter, and it similarly has no solid surface beneath its cloud layers. One curious fact often noted is that Saturn is the least dense of the planets. Its overall density is even lower than that of water. If there were a bathtub large enough, Saturn could theoretically float in it, a fanciful image that underscores its makeup as a giant ball of gas. The hallmark of Saturn is its rings, broad, flat sheets of countless particles orbiting the planet in unison. These rings are composed primarily of water ice, mixed with dust and rock, with particles ranging in size from tiny grains to boulders as large as houses. The main rings span over 270,000 kilometers in diameter, yet they are amazingly thin, in most places only tens of meters thick. When sunlight hits them, the rings shine bright and white, like a celestial halo. Gaps and divisions can be seen within the rings, caused by the gravitational influence of Saturn's many moons that shepherd the ring particles into patterns. The largest gap, called the Cassini division, separates the two most prominent ring bands. Up close, Saturn's ring system would appear as a glittering plain of ice and rock chunks, each racing around Saturn in its own orbit. Despite their grand appearance, the rings are not permanent. Over eons they may dissipate or coalesce into new moons, reminding us that even seemingly unchanging features of the solar system are dynamic on long-time scales. Saturn's atmosphere, though more subdued in color than Jupiter's, is still banded and dynamic. Buttery gold and butterscotch hues dominate, occasionally disrupted by white storm systems that erupt and spread. Every few decades, a gigantic storm called the Great White Spot appears in Saturn's clouds, encircling the planet and lasting for months before fading. High-speed winds, especially near the equator, rush through Saturn's upper atmosphere at about 1,800 kilometers per hour, even swifter than Jupiter's jet streams. At Saturn's north pole, a strange, long-lasting feature draws interest: a 6-sided jet stream forming a hexagon-shaped pattern in the clouds, large enough to fit 2 Earths across. This hexagon, with a rotating storm at its center, has persisted for decades, perhaps much longer, a peculiarity of Saturn's fluid atmosphere. Beneath the upper clouds, Saturn's gaseous layers transition with depth into hot, dense fluids, similar to Jupiter's interior, including a layer of electrically conducting metallic hydrogen. Saturn also has a powerful magnetic field, though weaker than Jupiter's, and it too produces auroras around its poles, shimmering in ultraviolet light above the cloud tops. Accompanying Saturn is a remarkable collection of moons, more than 80 at last count, each contributing to the story of the Saturnian system. The largest and most famous is Titan, a moon bigger than the planet Mercury. Titan is shrouded in a thick, orange-colored atmosphere so dense that it completely hides the surface from view. This atmosphere is mostly nitrogen, with a touch of methane. On Titan's frigid surface, around 179 degrees, that methane plays a role similar to water on Earth. Titan has rivers, lakes, and seas, but they are filled with liquid methane and ethane instead of water. Clouds of methane occasionally drizzle rain onto the icy ground, and a cycle of evaporation and condensation creates a weather system eerily parallel to Earth's hydrological cycle, albeit with different materials in play. When our spacecraft first landed on Titan and peered through the haze, it revealed a surprisingly Earth-like vista. A dim orange sky over a landscape of frozen ground strewn with rounded icy pebbles, and even what looked like a shoreline of a methane lake in the distance. Titan's thick atmosphere would allow a human to walk on its surface without a pressure suit, though the cold and lack of oxygen would be instantly deadly. And with the low gravity, one could imagine strapping on wings and flying through the dense air with a running leap. Titan is a world that, despite its alien chemistry and cold, offers a familiar geography of rivers and lakes. Beneath its icy crust may lie an internal ocean of liquid water, adding to the potential for harboring the ingredients of life. Another intriguing moon of Saturn is Enceladus, a small, bright, ice-covered sphere only about 500 kilometers across. Enceladus looks like a shiny snowball, reflecting most of the sunlight that hits it. For a long time, it seemed unremarkable. But in 2005, our view of Enceladus changed dramatically. Geysers were discovered erupting from its south pole, great plumes of water vapor and ice particles shooting into space from cracks in the moon's crust. These geysers suggest that Enceladus harbors a subsurface ocean of liquid water beneath its ice shell, kept liquid by heat generated from tidal interactions with Saturn. The erupting plumes feed material into one of Saturn's rings, the diffuse E-ring, and have allowed spacecraft to sample their composition directly, finding water, simple organic molecules, and tiny grains of rocky material from the moon's interior. This makes Enceladus another compelling candidate in the search for extraterrestrial life, as it provides a direct window into a potentially habitable environment below the surface. Imagining standing on Enceladus's surface near the South Pole, one would see icy jets silently spraying into the starry darkness, the faint light of distant Saturn and the sun glinting off the frozen landscape. From Enceladus's perspective, Saturn would hang in the black sky with its rings on full display, a majestic view suspended above the horizon, casting a pale golden light on the frozen terrain. Saturn's other moons each have their own stories. There is Iapetus, half of which is as bright as snow and the other half as dark as coal, giving it a striking two-toned appearance that puzzled astronomers for centuries. There is Rhea, an airless, cratered ball of ice and rock, and Tethys, with a giant canyon, the Ithaca Chasma, spanning much of its hemisphere. Mimas, a smaller moon, bears a huge impact crater that makes it resemble the Death Star from fiction. Dozens more tiny moonlets dance within or just beyond the rings, shepherding ring particles and creating ripples in the ring's structure. Each moon adds a piece to Saturn's intricate gravitational ballet. The interactions between the moons and rings make Saturn's system a complex, living laboratory of orbital dynamics and history. In recent times, the Cassini spacecraft spent 13 years orbiting Saturn, giving us an intimate tour of this system and even flying through Enceladus's geysers to sample their makeup. Through Cassini's eyes, we witnessed Saturn's wonders up close, deepening our understanding and appreciation of the ringed world. Drifting away from Saturn, we watch the golden planet grow smaller, its rings thinning to a delicate line before vanishing from view. The sun is more distant now, and the warmth and light continue to fade. Ahead, the outer solar system stretches toward the realm of the ice giants. The next planets on our voyage, Uranus and Neptune, await us on the cold, dim frontier far from the sun. At the far edge of the planetary realm lie the two ice giants, Uranus and Neptune. These distant worlds are much colder and darker than the gas giants closer to the sun. They are called ice giants because a larger proportion of their makeup consists of ices in the form of water, ammonia, and methane, in addition to hydrogen and helium. From our vantage, Uranus and Neptune appear as small bluish-green disks through a telescope, but up close they are enormous planets in their own right, each about 4 times the diameter of Earth. Far from the sun, they receive only a faint fraction of its light and warmth, and their atmospheres form chilly, thin bands and faint clouds. Both Uranus and Neptune have a hazy aquamarine appearance due to methane gas in their upper atmospheres, absorbing red light and reflecting blue and green hues. The Sun from Neptune is merely a brilliant point of light, about 1/30th the apparent diameter it appears from Earth. Uranus, the 7th planet from the Sun, orbits at about 2.9 billion kilometers out, 19 AU. It takes 84 Earth years to complete one orbit. Barely visible to the naked eye under very dark skies, Uranus went unnoticed by ancient skywatchers due to its dimness and slow movement. Uranus is unique among the planets for its extreme axial tilt. It's tipped over about 98 degrees relative to its orbital plane. Essentially, Uranus rolls around the Sun on its side. This results in bizarre seasons. Each pole gets around 42 years of continuous sunlight, followed by 42 years of darkness as the planet circles the Sun. The cause of this tilt is likely a colossal collision with an Earth-sized object long ago that knocked Uranus over. Uranus's atmosphere is a bland blue-green, usually without the dramatic storms or colourful banding that we see on Jupiter or Saturn, though faint cloud features and occasional dark spots have been observed by telescopes. The planet is enveloped in an upper layer of hydrogen and helium gas with some methane, and deeper inside it likely has a slushy mixture of water, ammonia, and other ices above a small rocky core. Rings and moons accompany Uranus as well. Uranus has a set of thin, dark rings composed of dust and small boulders. They are much narrower and dimmer than Saturn's bright rings, and they encircle the planet above its equator, which, because of Uranus's tilt, is almost perpendicular to its path around the Sun. Uranus also has at least 27 known moons. Most of these moons are icy, dark bodies less than a few hundred kilometers across, but a few stand out. The largest moons, Titania, Oberon, Umbriel, Ariel, and Miranda, range from about 500 to 1,500 kilometers in diameter. Their surfaces are mixes of craters and canyons. Miranda, the innermost of those big moons, is especially odd. It has gigantic cliffs. One cliff, Verona Rupes, is estimated to be 20 kilometers high, and patchwork landscapes suggestive of past geological upheavals, almost as if the moon was shattered and reassembled. All of Uranus's moons, like the planet's rings, are tilted sideways along with the planet itself, orbiting around that sideways axis as Uranus rotates. One day on Uranus is about 17 hours. From a distance, Uranus and its ring moon system look like a celestial target tipped on its side, calmly cruising around the Sun. To date, only one spacecraft, Voyager 2, has visited Uranus in 1986 and Neptune in 1989, capturing our only close-up images of these remote worlds. One more step outward brings us to Neptune, the eighth and outermost major planet. Neptune orbits about 4.5 billion kilometers from the Sun, 30 AU, some 30 times the Earth-Sun distance. It takes Neptune 165 Earth years to orbit the Sun. A human would not live long enough to see a single Neptunian year. Neptune's existence was predicted by mathematicians before it was observed through a telescope in 1846, due to its subtle gravitational effects on Uranus. Neptune is similar in size and composition to Uranus, with a deep blue atmosphere rich in hydrogen, helium, and methane. But Neptune is notably more active in terms of weather. Despite receiving even less solar energy than Uranus, Neptune boasts the fastest winds in the solar system, with jet streams roaring at up to 2,000 kilometers per hour. When NASA's Voyager 2 spacecraft flew by Neptune in 1989, it observed a large dark storm about the size of Earth, which was dubbed the Great Dark Spot. This storm had vanished by the time the Hubble Space Telescope looked a few years later. But other dark spots have appeared and disappeared since, indicating that Neptune's atmosphere is constantly changing. Thin, wispy clouds of methane ice have been seen scooting around Neptune's atmosphere, casting shadows on the cloud layers below as they race past. Neptune's overall deep blue color and dynamic weather give it a haunting beauty on the fringes of the Sun's domain. Neptune has a set of faint rings and at least 14 known moons. By far the largest moon is Triton, a world that intrigues astronomers greatly. Triton is about 2,700 kilometers across, not much smaller than Earth's moon, and has a pinkish, frozen surface. Uniquely, Triton orbits Neptune in the opposite direction of Neptune's rotation, a retrograde orbit, suggesting that Triton was likely a captured object from the distant Kuiper belt, rather than forming alongside Neptune. Triton is an extremely cold place, with a surface temperature around 235 degrees, 391 degrees. Yet when Voyager 2 flew by, it saw evidence of activity, geyser-like plumes erupting from Triton's surface, likely caused by the feeble sunlight warming subsurface nitrogen ice that then vents gas through cracks. Triton's surface also has a strange cracked terrain, sometimes called cantaloupe terrain, due to its dimpled appearance. It's thought that Triton, like the icy moons of Jupiter and Saturn, might have a subsurface ocean deep beneath its frozen crust, kept slightly warm by internal heating and the tug of Neptune's gravity. Whether or not that is true, Triton clearly has some level of geological activity, even in the deep freeze so far from the Sun. With Triton, Neptune's gravitational domain seems to reach out and grab a piece of the distant icy regions of the solar system. Beyond Neptune's orbit, the solar system continues into a vast expanse of small frozen worlds. The two ice giants mark the end of the traditional planets, but not the end of the Sun's family. As we prepare to leave Neptune behind, we turn our attention to those distant, dim objects, dwarf planets, comets, and asteroids, that populate the fringes and fill the gaps between the major worlds. Leaving behind the last of the major planets, we find that the solar system still has much more to offer. In the vast space between and beyond the planets are countless smaller worlds, remnants and cousins of the planetary formation process. These include dwarf planets, asteroids, comets, and other icy bodies that quietly wander in the darkness. Though diminutive in size, they carry great significance, preserving clues about the solar system's birth and serving as cosmic messengers that occasionally visit Earth's skies. Between Mars and Jupiter lies the main asteroid belt, a wide expanse containing millions of rocky fragments. Here float bits of rock and metal left over from the dawn of the solar system. These are pieces that never managed to form into a planet, largely due to the disruptive gravity of nearby Jupiter. the asteroids range from tiny pebbles only a few meters across to substantial protoplanets hundreds of kilometers wide. The largest object in the belt is Ceres, a dwarf planet about 950 kilometers in diameter, big enough for its gravity to have molded it into a round shape. Ceres contains water ice beneath its crust and even shows signs of past geologic activity, such as mysterious bright salt deposits gleaming on its surface. Most asteroids, however, are irregularly shaped, cratered, and inert, true rubble from the solar system's early days. They tumble silently through space, occasionally colliding with each other or being nudged by gravitational resonances into new orbits. Gravity on these small worlds is feeble. A person could hop and perhaps not come down again, escaping the asteroid entirely if not careful. From time to time, asteroids do leave the main belt. Some, known as near-Earth asteroids, wander into the inner solar system and even cross Earth's orbit. Over the eons, impacts from such asteroids have peppered the moon and planets, carving out craters and sometimes influencing the course of life on Earth. It is believed that long ago, asteroid and comet impacts delivered a significant portion of the water and organic molecules that helped create Earth's oceans and set the conditions for life. On the flip side, large asteroid impacts have also caused catastrophic changes. Famously, a roughly 10-kilometer asteroid struck Earth 66 million years ago, contributing to the end of the age of dinosaurs. Yet not all encounters are destructive. As Earth plows through the dusty trails left by comets or fragments of asteroids, we are treated to gentle meteor showers, those annual spectacles of shooting stars silently streaking across the night sky. Farther out, beyond the orbit of Neptune, we enter the Kuiper Belt, a distant ring of icy bodies encircling the Sun. This region is home to a multitude of dwarf planets and smaller frozen objects. Pluto is the most famous of these. Once considered the 9th planet, Pluto is now recognized as one of the largest members of this outer belt. It orbits the Sun at an average distance of about 5.9 billion kilometers, 39 AU, and takes 248 years to complete one orbit. Pluto is a complex world in its own right. It has mountains made of hard water ice, smooth plains of frozen nitrogen, a tenuous blue atmosphere that expands when Pluto is closest to the Sun, and can freeze and collapse onto the surface when Pluto is farthest from the Sun, and a striking heart-shaped region on its surface, observed by the New Horizons spacecraft in 2015. On Pluto's surface at noon, the Sun is only a very bright star in a black sky, providing light akin to deep twilight on Earth. Charon, Pluto's largest moon, about half Pluto's size, would loom large in the sky when visible, and the landscape would be illuminated by a faint, icy glow. Pluto also has 5 known moons, the largest of which, Charon, is so big that Pluto and Charon essentially form a double dwarf planet system, twirling around a point in space between them. The discovery that Pluto is not alone, but one of many similar bodies, sparked a reclassification of what constitutes a planet. Along with Pluto, several other distant worlds, such as Eris, Makemake, and Haumea, are now designated as dwarf planets. Each has its own character. Eris is nearly Pluto's twin in size but orbits farther out. Haumea is elongated and spins rapidly, with a day lasting only 4 hours. It even has a faint ring system of its own. Makemake is icy and bright, and has at least one small moon. These frozen worlds dot the Kuiper Belt and beyond, forming a bridge between the realm of the major planets and the vast interstellar spaces beyond our solar system. Comets are another class of small world, essentially cosmic icebergs that travel on elongated orbits. They spend most of their time in the deep freeze far from the Sun, but occasionally one journeys inward. As a comet approaches the Sun, the increasing warmth causes its ices to sublimate, turn directly from solid to gas, releasing gas and dust that billow out around the comet's nucleus. Solar radiation and the solar wind then push this material out into a long tail that can stretch for millions of kilometers. It's this bright tail, along with a fainter bluish ion tail, that makes comets such lovely and eerie sights in our skies. Comet Hale-Bopp in 1997, for example, remained visible for months, its dual tails captivating skywatchers worldwide. In ancient times, comets were seen as omens, their sudden appearance and ghostly tails inspiring awe and superstition. Now we understand them as time capsules of the early solar system, shedding material each time they pass near the Sun. Some comets return periodically. Halley's Comet, for instance, swings through the inner solar system about every 75 years, and has been observed and recorded throughout human history. Others plunge inward from much greater distances, taking thousands or even millions of years to complete a single loop around the Sun. And some come just once, flying in from the depths of space, grazing the Sun, and then slingshotting away on paths that will never bring them back. Where do these comets originate? Many hail from the Kuiper Belt and are knocked into the inner solar system by gravitational nudges, becoming the short-period comets that frequently grace our skies. But the most distant reservoir of comets is thought to be the Oort cloud, a vast, spherical shell of potential comets surrounding our solar system, perhaps 50,000 to 100,000 astronomical units away. That's up to nearly 2 light years, a substantial fraction of the distance to the nearest stars. This distance is on the order of a light year, meaning the Oort cloud may stretch nearly halfway to the nearest other star beyond our Sun. The Oort cloud likely contains trillions of icy bodies, the leftover debris from the solar nebula, flung to the far fringes by gravitational interactions long ago. Occasionally, a passing star or the tidal forces of the Milky Way disturb one of these distant icy objects, sending it on a slow voyage toward the inner solar system. By the time it arrives, we see it as a newcomer, a long-period comet blazing a brief trail across our sky with a luminous tail. After swinging around the Sun, it may return to the cold dark for thousands or even millions of years. Or it might be ejected entirely, cast off to wander the galaxy. All these small worlds, the asteroids, the dwarf planets, the comets, and the countless fragments in between, form a cosmic debris field that both separates and connects the larger planets. They are the leftover building blocks, the ancient archives of the solar system's formation and evolution. Each meteor that burns up in Earth's atmosphere, each comet that unfurls its tail in the sky, each space rock quietly circling in the dark, is a reminder of the solar system's long history and dynamic nature. As we drift farther out, past the Kuiper Belt and through the hypothetical Oort cloud, the Sun itself begins to wane to a very bright star behind us. We have nearly reached the edge of our solar system's influence, where the solar wind gives way to the interstellar environment of the galaxy. In fact, in 2012, Voyager 1 became the first spacecraft to cross into interstellar space, having travelled for nearly 35 years to slip out of the Sun's immediate influence. Beyond lies the domain of other stars. The endless night of interstellar space beckons us onward, with the promise of new suns and new worlds in the chapters ahead. Beneath a clear night sky, far from city lights, a soft band of light sweeps across the darkness overhead. This gauzy glow, stretching from horizon to horizon, is the Milky Way, our home galaxy, seen from within. For countless generations, people gazing upward have wondered about this misty river of light. The ancient Greeks imagined it as milk from the breast of a goddess, hence the name Milky Way. Others called it a celestial river, or the backbone of night. Every culture looked up and found meaning in that band of light. Today we know it's not a cloud at all, but the combined glow of billions of distant stars. We live inside this grand collection of stars, gas, and dust, orbiting a common center across unimaginable distances. In the fullness of time and space, the Milky Way reveals itself as a spiral galaxy, a vast rotating disk with curving arms of stars. If we could see our galaxy from the outside, it would resemble a giant pinwheel made of hundreds of billions of suns. Our Sun is just one of those stars, located about halfway out from the galactic center on a minor spur between larger spiral arms. Even at our position far from the crowded core, we are gravitationally bound into the Milky Way's rotating grand design. For our solar system to complete a single journey around the galaxy's center takes roughly 240 million years. In the time it takes for our Sun to make one orbit, continents drift, and life forms on Earth rise and fall. So vast is our galaxy that even moving at hundreds of kilometers per second, the Sun requires nearly 250 million years to circle it once. Through this cosmic dance, the Sun and its planets move along, bound by the gravity that holds the Milky Way together. At the heart of the Milky Way lies a dense, mysterious central region. There, countless stars crowd together in a swollen bulge around the core. Hidden in the darkness of this core is a supermassive black hole called Sagittarius A. 4 million times the mass of our Sun, this invisible giant anchors the galaxy with its intense gravity. Stars near the galactic center orbit at incredible speeds, whipping around the unseen black hole in tight, fast loops. Though the black hole itself emits no light, its presence is betrayed by the whirling motions of stars and a faint radio glow at the center of everything. Spiraling out from the center are the Milky Way's arms, vast swathes of stars, gas, and dust curving around the galaxy. These spiral arms are like stellar nurseries, rich with clouds of gas where new stars ignite. Our Sun resides in a smaller branch known as the Orion Arm, nestled between major arms. Along these arms, bright young stars and glowing nebulae trace the pattern of the galaxy, marking regions where it continues to form new suns. In contrast, older stars abound in the central bulge and the extended halo of the galaxy, telling of ancient times when the Milky Way was young. The Milky Way stretches well over 100,000 light-years from end to end. Its shining disk is relatively thin, only about 1,000 light-years thick in the main stellar layer, but it bulges outward in the middle, where the oldest stars congregate in the galactic bulge. Surrounding the visible disk is an even larger halo of invisible matter and a sprinkling of ancient star clusters. Within this halo roam the oldest members of our galactic family, globular clusters of old stars that formed when the galaxy itself was in its infancy. In total, the Milky Way is home to an astonishing number of stars, on the order of a few 100 billion. Scattered among these stars are countless planets, including our own Earth. It's estimated that planets are at least as numerous as the stars themselves. Our galaxy also contains drifting clouds of interstellar dust, great arcs of nebulae, and the remnants of stellar explosions. All these components weave together under gravity's guidance, composing the dynamic ecosystem of our galaxy. The Milky Way does not drift alone. Smaller satellite galaxies accompany our own, bound by gravity and orbiting it over billions of years. Among them are the large and small Magellanic Clouds, irregular dwarf galaxies visible as fuzzy patches in the southern hemisphere's night sky. Dozens of these diminutive galactic companions circle the outskirts of the Milky Way, their stars occasionally mingling with those at the edge of our galaxy during close passes. In time, some may even be absorbed into the Milky Way, adding their light to our galactic population. For a long while, living inside the Milky Way meant we could only guess its true shape and size. Like being deep in a forest and trying to map its extent, early astronomers saw dense clusters of stars in some directions and dark gaps in others. With the invention of telescopes and careful measurement, we gradually discerned our galaxy's spiral structure and our place within it. Now we understand the Milky Way as a rotating, barred spiral galaxy, with our sun riding along one of its sweeping arms. Every star we see in the night sky, without exception, is part of the Milky Way. The galaxy is our cosmic neighborhood, the stage for our sun's journey through space. Encircling the center for over 4 billion years, our sun has made about 18 orbits around the Milky Way since it was born. In that time, the galaxy itself has grown and changed. It has swallowed smaller galaxies and continued forming new stars from its reservoirs of gas. In the grand timeline of the cosmos, the Milky Way preserves the history of countless stars that lived and died long before our sun ever came to be. Within this immense galactic home lie regions of remarkable beauty and significance. Scattered across the spiral arms are luminous nebulae, immense clouds where stars are born and where stars die, and clusters of stars gathered in celestial communities. These are the Milky Way's gardens, where cosmic blooms take shape. To journey onward, we venture into these nebulae and clusters to see how stars come into being and how they sometimes group together, painting our galaxy with their light. Within the Milky Way, nebulae are among the most captivating sights of all. A nebula is a vast cloud of gas and dust drifting between the stars, a cosmic cloud that can give birth to new stars or mark the grave of old ones. In these celestial clouds, the life cycle of stars plays out on a colossal scale. Some nebulae are glowing nurseries where young stars are just beginning to shine. Others are ghostly remnants left behind when a star dies, its material cast back into space to seed future generations of suns. In star-forming nebulae, dense knots of gas gradually collapse under gravity's pull. As the gas falls inward, it heats up, and a new star ignites at the core. Surrounding the newborn star, leftover gas and dust flatten into a whirling disk, raw material for potential planets and moons. One of the most famous of these stellar nurseries is the Orion Nebula, a hazy patch in the sword of the constellation Orion. Here, about 1/300 light-years from Earth, hundreds of baby stars illuminate the gas around them, creating a luminous tapestry visible even in small telescopes. The Orion Nebula is just one example of the Milky Way's many nurseries, where, at this very moment, stars are taking shape. In the Eagle Nebula, for example, towering pillars of gas, nicknamed the Pillars of Creation, are being sculpted by the intense radiation of newborn stars, a testament to the galaxy's ongoing creativity. Elsewhere in the galaxy, different kinds of nebulae tell other chapters of the stellar story. When a star like our Sun nears the end of its life, it sheds its outer layers into space, creating what is known as a planetary nebula. Despite the name, these nebulae have nothing to do with planets. Early astronomers named them for their round, planet-like appearance in small telescopes. A planetary nebula forms a beautiful shell or bubble of gas, expanding outward from the dying star at the center. The star's core remains behind as a white dwarf, a hot ember of what once was a sun. Over time, the glowing gas disperses, enriching the surrounding space with elements that will one day become part of new stars and planets. For far more massive stars, the end comes in a cataclysmic supernova explosion. In a supernova, a star blows itself apart, briefly outshining entire galaxies. The debris racing outward from such an explosion forms a supernova remnant, another type of nebula. The famous Crab Nebula, for instance, is the expanding cloud of gas and dust left from a supernova observed by humans nearly 1,000 years ago. Inside it, the crushed core of the original star survives as a pulsar, a rapidly spinning neutron star sending out pulses of energy. Supernova remnants, like the Crab Nebula, are the universe's way of recycling matter. The violent death of a star scatters heavy elements like carbon, oxygen, and iron into space, where they can become part of new cosmic creations. Indeed, every atom of calcium in our bones and iron in our blood was forged in such stellar explosions, long before the Sun and Earth existed. Not all nebulae shine with their own light. Some are dark nebulae, thick, light-blocking clouds of dust that obscure the stars behind them. These dark nebulae appear as inky silhouettes against a brighter starry background, like cosmic storm clouds. Within their cold and shadowy interiors, stars may be quietly forming, hidden from our view until their light breaks through. One well-known dark nebula is the Horsehead Nebula, a dense patch of dusk and gas, whose distinctive shape stands out as a dark outline in front of a glowing hydrogen cloud. Such nebulae remind us that much of our galaxy is filled with dust, an essential ingredient for planet building, even if it often veils the light of distant stars. Amid these clouds of gas and dust, stars are often born not in isolation, but in groups. A single giant molecular cloud, an enormous reservoir of cold gas, can give birth to an entire cluster of stars. These sibling stars, born from the same cloud, form what we call a star cluster. In the Milky Way, we find two very different kinds of star clusters: open clusters and globular clusters. Open clusters are youthful gatherings of stars. They generally contain a few dozen to a few thousand stars that formed together relatively recently, in cosmic terms. These stars are loosely bound by gravity, and over time they tend to drift apart. One example of an open cluster is the Pleiades, often called the Seven Sisters, which adorns the night sky in the constellation Taurus. The Pleiades is about 100 million years old, young for stars, and contains several hundred stars, though only a handful are visible to the naked eye. Shining with a bluish light, its brightest stars are hot and massive, and a delicate haze of leftover nebula dust can still be seen around them in photographs. Open clusters like the Pleiades are sprinkled throughout the galactic disk, often marking places where a nebula recently gave birth to new stars. Over the course of tens or hundreds of millions of years, the stars in an open cluster gradually wander away as each follows its own path around the galaxy. Many stars in our night sky were likely born in clusters that have long since dispersed. Our own Sun may have been part of an open cluster in its infancy, sharing its birth with sibling stars that have now scattered across the Milky Way. The fate of open clusters is to disperse, contributing their stars to the wider galaxy, whereas another type of cluster remains bound for far longer. Globular clusters are a different kind of stellar gathering. They are ancient, tightly packed spheres of stars that orbit in the far outskirts of our galaxy. A globular cluster can contain hundreds of thousands, even millions, of stars crammed into a ball only a few hundred light years across. In the heart of a globular cluster, stars are so densely packed that they would fill the sky of any planet there with a glittering swarm of suns. These clusters are also extremely old. Many are over 10 billion years old, meaning they formed when the Milky Way itself was young. The stars in globular clusters tend to be smaller, redder, and older than our Sun, having burned for eons. Because they formed so early, they contain fewer of the heavy elements that younger stars, like the Sun, incorporate. Yet these venerable clusters have survived through the eons, orbiting quietly in the galactic halo. The Milky Way has over 100 known globular clusters, and they serve as living fossils of the early universe within our galaxy. For example, the Hercules globular cluster, also known as M13, is a great ball of stars around 22,000 light-years from Earth, visible in a small telescope. It contains hundreds of thousands of ancient stars, a swarm that has been shining since before Earth was formed. When we observe such clusters, we are witnessing a relic of how star formation occurred in the deep past. They are part of the Milky Way's extended family, orbiting well beyond the galaxy's main disk. Both nebulae and star clusters reveal the communal nature of stars. Stars often emerge together from shared clouds, and sometimes remain bound together for long stretches of time. In these celestial gardens, we see creation and community. Stars taking shape in glowing nebulae, and stars banding together in clusters. Each nebula and cluster is a snapshot of a particular moment in the life cycle of stars. Whether it's the fresh bloom of stellar birth, or the faded glow of an aging cluster holding onto ancient stars. As we drift through the Milky Way's tapestry of nebulae and clusters, we appreciate that our galaxy is constantly regenerating and evolving. New stars spark into existence as old ones fade away. Stellar families form and later disperse. The light from young clusters and the dim shine of aged stars both enrich the galaxy's story. Having admired these intimate wonders within our own galaxy, we now widen our view beyond the Milky Way. Our home galaxy, magnificent as it is just one island in a vast sea of galaxies. Beyond its starry borders lies the immense realm of other galaxies, each with its own stars, nebulae, clusters, and mysteries. The time has come to leave the Milky Way behind in our journey and set sail for these island universes far, far away. Beyond the edges of our Milky Way, vast oceans of space stretch out for billions of light years. Scattered across these depths are uncountable other galaxies. Each one is an island of stars in its own right, an island universe shining in the darkness. For a long time, we had no idea such distant galaxies even existed. Less than a century ago, many astronomers believed the Milky Way encompassed the entire universe. What appeared as faint, fuzzy patches of light in the night sky were assumed to be nearby clouds of gas or small clusters of stars. But as telescopes improved, evidence mounted that some of those spirals and smudges were far outside our own galaxy. In 1924, Edwin Hubble proved that the Great Andromeda Nebula was actually another galaxy, millions of light years away. This revelation expanded our cosmos enormously. The Milky Way was not alone, but one among countless galaxies in a vastly larger universe. Andromeda, our nearest large galactic neighbour, is a spiral galaxy quite similar to the Milky Way. It lies about 2.5 million light-years from us, so distant that the light we see from Andromeda today left it when early humans were first shaping simple stone tools. Andromeda is immense. It may contain as many stars as the Milky Way, or even more. Through a telescope, it appears as a delicate, elongated smudge of light with a bright core. Our two galaxies, the Milky Way, and Andromeda, are actually moving toward each other, destined to meet. In roughly 4 billion years, they will begin to merge in a slow gravitational dance that will take another few billion years to complete. Eventually, the two spirals will coalesce into a single, larger galaxy. In that far-off future, the night sky will change dramatically, illuminated by the glow of new star formation as the galaxies collide. Over time, the two galaxies' central black holes will spiral together and merge, settling into the core of a unified new galaxy. After the frenzy of merging subsides, what remains will likely be a giant elliptical galaxy where two spirals once shone. For now, however, Andromeda remains a serene, majestic spiral in the darkness, one of the very few galaxies visible to the unaided human eye under truly dark skies. Andromeda is just one member of a small gathering of galaxies to which the Milky Way belongs. Along with a third sizable spiral galaxy called Triangulum M33 and dozens of smaller dwarf galaxies, we form what is known as the local group. All the galaxies in the local group lie within a few million light-years of each other, bound in a loose association by gravity. Some of the dwarf galaxies in the local group orbit our Milky Way. We have already met two of them, the Magellanic Clouds, while others orbit Andromeda. In time, many of these tiny galaxies may merge into their larger neighbours. The local group itself is on a journey, drifting toward a much larger assembly of galaxies known as the Virgo cluster. The Virgo cluster, roughly 50 million light-years away, contains well over 1,000 galaxies. At its heart are giant elliptical galaxies, enormous balls of stars far larger than the Milky Way. These massive ellipticals likely formed from many smaller galaxies merging over billions of years. Scattered around them are spiral galaxies, lenticular, lens-shaped galaxies, and irregular galaxies of all sizes. Our local group sits on the outskirts of this cluster. The Virgo cluster is just one part of an even larger structure called the Laniakea supercluster, a tremendous collection of galaxy groups and clusters, including Virgo. This supercluster stretches over 500 million light-years and contains perhaps 100,000 galaxies. The name Laniakea means immeasurable heaven in Hawaiian, an apt description for such an immense region of the cosmos. The Milky Way, along with its nearby companions, is like a tiny suburb within the vast Laniakea supercluster. As we map the distribution of galaxies on the largest scales, a remarkable cosmic architecture emerges. Galaxies are not scattered randomly. They gather in groups and clusters, and those clusters form part of larger patterns. This grand arrangement is often called the cosmic web. Imagine a web-like network spanning the cosmos, where each node is a cluster of galaxies, and each thread is a chain of galaxies stretching for hundreds of millions of light-years. Our local group and the Virgo cluster are nodes in this cosmic web, connected by filaments of galaxies. Between these filaments lie enormous voids, vast empty regions with few or no galaxies. On such scales, the universe resembles a sponge or honeycomb, with matter clumped along filaments around tremendous empty spaces. It is humbling to recognize that the universe is structured on such scales, far beyond human comprehension, yet discernible through our observations. The number of galaxies in the observable universe is truly staggering. A long, deep exposure with the Hubble Space Telescope famously revealed thousands of galaxies in a patch of sky so tiny it could be covered by a grain of sand held at arm's length. Everywhere we look, even in the darkest, most empty regions of sky, galaxies abound when our instruments are sensitive enough to detect them. By current estimates, Hundreds of billions of galaxies inhabit the observable universe, perhaps as many as 2 trillion. And beyond the horizon of what we can see, there may lie countless more. Each galaxy itself can host billions or trillions of stars. The sheer scale of it all defies easy comprehension. For every single star in our Milky Way, there might be an entire galaxy out there, shining with its own multitude of stars. Galaxies also come in diverse forms. Many, like the Milky Way and Andromeda, are elegant spiral galaxies, flat, rotating disks with graceful arms winding out from a bright central core. Spirals usually contain plenty of gas and dust and actively birth new stars, especially in their arms. Other galaxies take a different shape. Elliptical galaxies, which range from nearly round to elongated ovals. Elliptical galaxies are populated mostly by older stars and have very little gas or dust, so new star formation within them has nearly ceased. They emit a steady, diffuse light, often with a golden or reddish hue from their aging stars. The largest galaxies in the universe are giant ellipticals, some 10 times more massive than the Milky Way. These leviathans likely grew by consuming smaller galaxies over time and typically sit at the centers of galaxy clusters. Then there are irregular galaxies, which lack any clear structure. Many irregulars are dwarf galaxies that have been warped by the gravitational pull of larger neighbors. Collisions or close passes between galaxies can twist them into chaotic shapes, drawing out long tidal tails of stars and gas. The Magellanic Clouds orbiting our Milky Way are examples of small galaxies with irregular forms. Though much smaller than a grand spiral, each Magellanic Cloud still contains billions of stars. Galaxy interactions are common over cosmic timescales. Given enough time, nearly every galaxy will eventually encounter another. When galaxies collide, it's more like a slow dance than a violent crash. Individual stars almost never hit one another directly because of the vast distances between them. Instead, the galaxies sweep through each other, and their mutual gravity stretches and distorts their shapes. Gas clouds slam into gas clouds, triggering bursts of new star formation as they merge. Over millions of years, 2 colliding galaxies may settle into a single, larger galaxy, their original forms forever altered by the encounter. Our own future offers an example of such cosmic interaction. As mentioned before, the Milky Way and Andromeda are expected to collide in about 4 billion years. Long before the final merger, the night sky from Earth, assuming Earth still exists and has observers then, will change dramatically. Andromeda will grow larger and more spectacular in the sky as it approaches. When the galaxies begin to merge, brilliant new regions of star formation may light up the heavens. The supermassive black holes at each galaxy's core will spiral toward one another and eventually coalesce into an even more massive black hole. After perhaps billions of years of slow gravitational dance, the end result will likely be a giant elliptical galaxy, where once there were 2 majestic spirals. Though this event lies in the distant future, it shows that galaxies are dynamic, ever-evolving systems. Even isolated galaxies change over time. Young galaxies in the early universe often appeared irregular or clumpy, forming stars at a furious rate. As galaxies mature, their star birth slows. They use up or lose much of their gas, and the brilliant blue glow of youth fades to a softer shine. A spiral galaxy may gradually alter its appearance over billions of years, or it might merge with others and become an elliptical. By observing galaxies at different distances, and thus at different eras of cosmic time, we can trace these changes. With modern telescopes, we glimpse galaxies as they were billions of years ago, when the cosmos was young. Those distant, early galaxies show us how smaller systems merged and grew into the majestic galaxies we see around us today. The saga of galaxies is one of continuous change, from the first faint aggregations of stars to the grand assemblies we inhabit now. As we survey this immense panorama of galaxies, we find many answers, yet still more questions. We've learned that most large galaxies harbour a supermassive black hole at their centre, an object millions or even billions of times the Sun's mass. We also know that galaxies are enveloped in vast halos of invisible dark matter that hold them together and influence their motions. We notice patterns in the arrangement of galaxies on cosmic scales, and we see hints of the universe's beginning in the faint background glow and the distribution of galaxies across space. Yet fundamental mysteries remain. What is the true nature of the dark matter that outweighs the visible stars? How did the very first galaxies coalesce from the nearly uniform early cosmos? These questions lead us naturally to deeper cosmic mysteries. Having sailed among the island universes and marveled at their scale, we turn our attention to the curious phenomena that push the boundaries of our understanding. Phenomena like black holes and the unseen forces shaping the cosmos. It is time to venture into the dark heart of cosmic mysteries. Throughout our journey, we've glimpsed the influence of unseen phenomena. Perhaps the most famous cosmic mystery is the black hole, a region of space where gravity is so overwhelming that nothing, not even light, can escape. Black holes are the ultimate abyss. They form when a massive star collapses under its own weight at the end of its life, or when several stars' remnants merge into one. The result is an object so dense that it creates a deep well in the fabric of space and time. Anything that ventures too close is trapped forever behind the black hole's invisible boundary, known as the event horizon. For a long time, black holes were purely theoretical, a strange prediction of Einstein's general theory of relativity. Now we have ample evidence that they are real. In fact, a supermassive black hole sits at the centre of our Milky Way, and virtually every large galaxy harbours one at its core. These behemoths can reach mind-boggling sizes. The black hole in the galaxy M87, whose shadow was imaged by the Event Horizon Telescope, weighs billions of times more than the Sun, and has an event horizon larger than our entire solar system. Yet despite their mass, black holes are compact. And yet, what lies inside a black hole remains unknown. The laws of physics, as we know them, break down at the central singularity of a black hole, where density becomes effectively infinite. Some scientists have speculated that black holes might even be gateways to other parts of spacetime, or to other universes, through hypothetical wormholes. While there is no evidence for such exotic pathways, the mere existence of black holes forces us to grapple with the most extreme conditions nature can offer. What would it be like near a black hole? As an object falls closer, the pull of gravity grows rapidly stronger. Time itself begins to slow down relative to the outside universe. To a distant observer, an object falling toward the event horizon appears to move ever more slowly, growing redder and dimmer, never quite vanishing. But from the object's own perspective, it rushes inward and crosses the horizon, unable to turn back. The tidal forces near a black hole can be deadly, stretching and compressing matter in a process poetically called spaghettification. Anything that crosses the event horizon, be it a star or a spacecraft, is ultimately torn apart and added to the black hole's hidden mass. Black holes can be elusive because, by definition, they emit no light of their own. However, we detect them through their powerful effects on the environment. Matter spiraling into a black hole can form a superheated accretion disk, glowing brightly in X-rays and other radiation before it passes the point of no return. Some black holes, especially the supermassive ones at galactic centers, can power quasars, those extremely luminous beacons visible across the universe, caused by torrents of energy from gas falling into the hole. In our own galaxy, scientists have tracked stars whipping around an unseen object at incredible speeds near the center. This revealed the presence of our central black hole, Sagittarius A. And in a triumph of technology, astronomers captured a direct image of a black hole's silhouette by observing the glowing ring of gas around M87's supermassive black hole, essentially seeing the shadow of the event horizon itself. Black holes also announce themselves in the ripples of spacetime. When two black holes collide and merge, they release an enormous burst of energy in the form of gravitational waves, vibrations in the fabric of spacetime that spread outward like ripples on a pond. In 2015, detectors on Earth first recorded these faint tremors from a collision of black holes over 1 billion light-years away. It was an awe-inspiring confirmation that even in darkness, the universe has ways of making its presence known. We had heard the sound of two black holes merging, a fleeting chirp in the detectors that signified the shaking of the cosmos itself. It's a reminder that our universe still holds deep secrets, waiting for inquisitive minds to unravel. As astonishing as black holes are, they are just one piece of the cosmic mystery. There are also forces and substances in the universe that we know exist, yet we cannot see or fully explain. One of these is dark matter, an invisible form of matter that far outweighs all the stars and galaxies we can see. Astronomers discovered signs of dark matter by observing how galaxies rotate and how clusters of galaxies hold together. The stars in a galaxy's outer regions move much faster than they should if only visible matter existed, as though some hidden mass is providing extra gravity. Similarly, galaxies in clusters move as if a huge amount of unseen mass is present. We call this unseen mass dark matter. Unlike ordinary matter, dark matter does not emit or absorb light. It reveals itself only through gravity. It may consist of exotic particles that barely interact with normal matter. Experiments in laboratories deep underground and sensors in space are searching for these mysterious particles. But so far, dark matter remains elusive. Dark matter is not some minor curiosity. It constitutes roughly 85% of the matter in the universe. In fact, the very structure of the cosmos depends on it. The gravitational pull of dark matter in the early universe helped draw ordinary matter into clumps, seeding the formation of galaxies and galaxy clusters. Without dark matter, the universe today would look very different, likely lacking the rich cosmic web of structure that we see. And yet, despite its importance, we still don't know exactly what dark matter is. It could be a new kind of subatomic particle outside the realm of the atoms and molecules that make up planets and people. Until we can detect it directly, dark matter remains a shadowy presence, literally shaping the universe while staying hidden in plain sight. As if that were not enough, there is an even stranger mystery at work on the grandest scale: dark energy. While dark matter pulls things together with gravity, dark energy has the opposite effect. It pushes the fabric of the universe apart. In the late 1990s, astronomers measuring the light from distant exploding stars, supernovae, made a shocking discovery. The expansion of the universe is speeding up. This was the opposite of what they expected, since gravity should have been slowing the expansion over time. The best explanation for this accelerated expansion is that some kind of repulsive force or energy is built into the very structure of space. A dark energy that permeates the universe. Dark energy is even more overwhelming in scale than dark matter, making up about 2/3 of the total content of the cosmos. Unlike dark matter, which clumps around galaxies, dark energy seems to operate uniformly across space, driving galaxies apart from one another. We don't feel dark energy in our daily lives, but on cosmic scales, it will determine the fate of the universe. If it continues to dominate, the universe will keep expanding faster and faster, growing ever colder and emptier over the eons. Yet we have almost no idea what dark energy actually is. It could be a property of the vacuum of space itself, the cosmological constant that Einstein once theorized, or it might hint at new physics, a dynamic field that changes over time. Unraveling the nature of dark energy is one of the greatest challenges in cosmology today. Together, dark matter and dark energy tell us that everything we find familiar, all the stars, planets, and galaxies, accounts for only a small fraction of the cosmos. The rest is this unseen matter and unknown energy, profoundly influencing the evolution of the universe. It's humbling to realize that we have mapped galaxies and detected black holes, yet the majority of the cosmos remains shrouded in mystery. With each discovery, from gravitational waves to the faint afterglow of the Big Bang, we peel back another layer, but new questions always emerge. Our exploration of black holes and the dark components of the universe underscores how much remains to be understood. But amid these grand mysteries, there are also nearer wonders to explore. Turning our gaze from the depths of space to the worlds circling distant stars, we search for something more familiar. Are there other planets out there like our own? The next leg of our journey takes us from cosmic darkness into the light of distant suns and the planets that orbit them, toward the discovery of far-off worlds, and perhaps even signs of life beyond Earth. Humanity has long wondered if other worlds exist beyond our solar system. For centuries, the stars were thought to be distant suns, but whether they had planets was pure speculation. That changed in the final decade of the 20th century. In 1992, astronomers found the first undeniable exoplanets, surprisingly, orbiting a pulsar, the corpse of an exploded star. Then in 1995 came a historic discovery, a planet circling a sun-like star, 51 Pegasi, about 50 light-years away. That planet turned out to be a hot Jupiter, a gas giant orbiting scorchingly close to its star. It was unlike anything in our own solar system, a clue that distant planetary systems could be very different from ours. In the early years of planet hunting, astronomers often used the subtle gravitational tug of planets on their stars to find them. By measuring tiny Doppler shifts in a star's light, a slight wobble in the star's motion, scientists inferred the presence of unseen planets. This radial velocity technique revealed many of the first exoplanets, including 51 Pegasi b. As technology improved, new methods like the transit technique used by the Kepler Space Telescope vastly accelerated the pace of discovery. Since those first finds, the floodgates have opened. We have now confirmed the existence of over 5,000 exoplanets, and the number grows every year. These alien worlds come in astonishing variety. Some are giant planets hugging so close to their stars that their year lasts only a few days, and their heat-blasted atmospheres stream away into space. Others are icy orbs, far from the warmth of their sun. We've found super-Earths, planets more massive than Earth, but smaller than Neptune, and mini-Neptunes that blur the line between rocky world and gas dwarf. Planets have been discovered around stars of all types, from stars larger and hotter than our sun, to tiny, cool red dwarfs that barely glow. It turns out that planets are common, the rule rather than the exception. One of the most fruitful methods of finding exoplanets has been the transit technique. By patiently watching the brightness of thousands of stars, telescopes like NASA's Kepler mission detected the tiny dips in light that occur when a planet passes in front of its star. Kepler observed a rich patch of sky for years and revealed a cosmic menagerie of planets. It discovered rocky worlds only slightly bigger than Earth, giant planets orbiting two star systems, and solar systems arranged very unlike our own. Thanks to these discoveries, we now estimate that our galaxy alone likely harbours billions of planets. On average, there may be at least one planet for every star in the Milky Way. Among the thousands of known exoplanets are some that capture our imagination, those that might most resemble Earth. Astronomers are especially interested in planets that lie in the habitable zone around their stars, the range of distances where temperatures could allow liquid water on a planet's surface. We have already found a number of rocky, Earth-sized planets orbiting in the habitable zones of their stars. For instance, Kepler 186f, discovered in 2014, was one of the first Earth-sized worlds identified in its star's habitable zone. It orbits a dim red dwarf star and receives about 1/3 the light Earth gets from the Sun, placing it in a cooler but possibly still temperate regime. Another remarkable system is TRAPPIST-1, a red dwarf star just 39 light-years away that has 7 known planets, at least 3 of which lie in the star's habitable zone. All 7 planets are roughly Earth-sized, and they orbit so close to their faint sun that their years last only a few days to a couple of weeks. While red dwarf stars are smaller and cooler than the Sun, they are by far the most common type of star in our galaxy. This suggests there could be countless Earth-sized planets around such stars. The TRAPPIST-1 system offers a tantalizing example of how many worlds might be out there. Some possibly with the right conditions for water and maybe even life. Of course, habitable zone only means a planet could have the right temperature for liquid water. It doesn't guarantee a world is actually habitable or Earth-like. Many other factors play a role: a planet's atmosphere, its magnetic field, its chemical makeup, and the temperament of its parent star. Red dwarf stars, for example, often emit powerful flares that could strip a nearby planet's atmosphere. Still, the possibility remains that some exoplanets might have environments where life as we know it could thrive. Scientists are developing ways to probe exoplanet atmospheres for signs of water vapor, oxygen, or other gases that might hint at biological activity. The James Webb Space Telescope, launched in 2021, now allows us to analyze the light filtering through exoplanet atmospheres and detect some of these key molecules. In the coming years, we hope to find telltale indicators, perhaps an unexpected abundance of oxygen or a whiff of something like chlorophyll, that could suggest the presence of life on a distant world. Beyond the search for life, exoplanet science has broadened our understanding of how planetary systems form and evolve. We've observed systems with giant planets parked near their stars, suggesting that planets can migrate from where they originally formed. We've found planets in tight orbits around double star systems, showing that nature finds ways to make planets even under the glow of twin suns. There are even rogue planets wandering the galaxy alone without a star, likely ejected from their birth systems. Every new discovery adds a piece to the puzzle of how our own solar system fits into the wider tapestry of worlds. The diversity of worlds out there is truly breathtaking. Consider a planet like Kepler 16b, where 2 suns set over the horizon each day, not unlike the fictional world of Tatooine in Star Wars. Or take the class of planets called hot Jupiters, gas giants so close to their stars that their cloud tops are heated to thousands of degrees, perhaps raining molten glass or metal droplets in their searing skies. There may be water-rich, ocean planets, completely covered by global seas, or dense super-Earths with thick, heavy atmospheres. The cosmos seems to have crafted every variety of planet we can imagine, and many we never anticipated before we discovered them. Reality, it seems, has surpassed the imaginations of science fiction. The cosmos is teeming with worlds of every kind. For all the exotic planets astronomers have found, one in particular still stands out as uniquely precious: Earth itself. So far, no other planet we've observed can exactly match the life-friendly conditions of our home world, though a few come tantalizingly close. Earth remains, as far as we know, the only place in the universe that hosts living creatures. But the discovery of so many exoplanets, including some similar in size and orbit to Earth, suggests that our world is not alone in its general type. In the vastness of space, there may be many Earth-like planets, and on some of them, life may have arisen, and perhaps even evolved intelligence. It's a profound realization that softens the lonely darkness of the cosmic ocean. Maybe we are not solitary after all. As we gaze up at the night sky now, armed with knowledge, nearly every star we see is a sun with its own retinue of planets. The distances remain enormous. The nearest known exoplanet, Proxima b, is just over 4 light-years away. Even our fastest probes would take tens of thousands of years to reach that star, an illustration of the gulf between suns. Yet simply knowing these other worlds exist makes the universe feel more intimate. We can picture those distant planets orbiting their suns, and we can imagine that perhaps under alien skies, there could be beings who look toward our sun and wonder as well. The study of exoplanets is still young. Each new telescope and mission extends our reach, allowing us to find smaller and more distant planets. Future observatories will strive to directly image Earth-like worlds around nearby stars and search their atmospheres for signs of biology. We stand on the threshold of incredible discoveries. Having found that the night sky is filled with other worlds, our perspective on our own world has deepened. Earth is special, but it is not isolated. It is one planet among countless others in our galaxy. Now, to complete our journey, we shift our focus from individual stars and planets to the universe as a whole. We have explored the cosmos from our home galaxy out to distant galaxies, from stars and exoplanets to invisible mysteries. But how did all of this come to be? To answer that, we must travel back in time to the very beginning of the universe. It is time to witness the birth of the cosmos, follow its history, and ponder its ultimate destiny. To understand the grand story of the cosmos, we must indeed journey back to the very beginning. The universe is thought to have begun about 13.8 billion years ago, in an event we call the Big Bang. At that moment, all of space, time, matter, and energy were compressed into an unimaginably hot, dense state. There was no light yet as we know it, no atoms, not even the simplest particles, just a seething storm of pure energy and primordial substance. Then, in a fraction of a second, the infant universe expanded rapidly. Space itself blew up like a balloon, cooling as it grew. In that brief instant, a process called cosmic inflation, any tiny irregularities were smoothed out, setting the stage for the mostly uniform universe we see today. As the universe expanded and cooled, energy began converting into matter. The fundamental building blocks of matter, quarks, electrons, and other subatomic particles, emerged from the fiery plasma. Within the first second, some of those quarks combined to form protons and neutrons. The newborn universe was still incredibly hot and dense, a glowing fog of particles and light. In the first few minutes, a fraction of the protons and neutrons fused to create the nuclei of simple elements, mostly helium, along with a trace of lithium, while the rest remained as hydrogen nuclei, protons. After that brief period of nuclear fusion, the universe was left with a primordial mix of about 3/4 hydrogen and 1/4 helium by mass, the raw material for future stars. For the next 380,000 years or so, the universe was a brilliant, opaque fireball. Photons, particles of light, constantly scattered off free electrons in the hot plasma, unable to travel far. But as expansion continued, the temperature dropped to around 3,000 degrees. At this point, electrons combined with nuclei to form the first atoms, mainly hydrogen and helium. Suddenly, space became transparent. Light was free to stream across the cosmos. The glow from that moment, the afterglow of the Big Bang, still fills the universe today as the cosmic microwave background radiation. We observe it as a faint wash of microwaves coming from every direction, the oldest light in existence, a relic of when the universe was less than 500,000 years old. Over the last century, astronomers have gathered evidence for this cosmic origin story. In the 1920s, Edwin Hubble observed that distant galaxies are receding from us. Their light shifted to longer wavelengths, clear proof that space itself is expanding. In 1965, Arno Penzias and Robert Wilson discovered the cosmic microwave background, the faint afterglow of the Big Bang's fireball, confirming a key prediction of the theory. Even the observed proportions of hydrogen and helium in the universe align with what we expect from those first few minutes of primordial fusion. Piece by piece, these clues have allowed us to reconstruct the 13.8 billion year history of the cosmos. With the primordial fog lifted, the universe entered a dark age. For millions of years, there were not yet any stars or galaxies, only vast clouds of cooling hydrogen and helium, slowly gathering under gravity's influence. The initial expansion had left tiny ripples of higher density within this gas. Over time, these denser pockets pulled in more matter, growing steadily. Dark matter provided additional gravitational pull in these regions, helping the gas clump faster. After a few 100 million years, the first stars ignited. These stars were likely much more massive and hotter than our Sun. They burned their fuel quickly and died in powerful supernova explosions, spewing heavier elements like carbon, oxygen, and iron into space, the seeds for future planets and life. As more stars formed and died, the first galaxies took shape. By about 1 billion years after the Big Bang, the universe was filled with infant galaxies, smaller and more irregular than the grand spirals and ellipticals we see today. Galaxies merged and evolved over time, growing larger and organizing into clusters. The cosmic web of filaments and voids became more pronounced. Star formations surged during this era. Young galaxies were churning out stars at a furious rate. Quasars, the brilliant beacons powered by voracious supermassive black holes, blazed from the centers of some galaxies, outshining all their stars. The cosmos in those early eons was a vibrant, turbulent place. Over billions of years, the universe continued to expand and mature. Galaxies settled into the forms we recognize: spirals, ellipticals, and irregulars. The overall rate of star formation began to decline as the most accessible gas was used up or locked into stars. Our own Milky Way galaxy formed during this period, gathering together countless smaller protogalaxies and star clusters. About 4.6 billion years ago, roughly 2/3 of the way from the Big Bang to today, one ordinary star in a quiet arm of the Milky Way was born: our Sun. Around it, a retinue of planets coalesced, including Earth. On that nascent Earth, conditions eventually allowed life to arise, a development that would, much later, enable a species of curious beings to look back and piece together this very history. While stars and planets were forming, the expansion of the universe was being influenced by a subtle competition between matter and something else. For the first few billion years, the mutual gravity of matter, both normal and dark, was slowing the expansion. But as space grew larger and emptier, an enigmatic force, dark energy, began to dominate. A few billion years ago, cosmic expansion stopped decelerating and began to accelerate. Distant galaxies started to push away faster and faster. Today, we measure this accelerating expansion and attribute it to dark energy, a still mysterious property of the universe that seems to be stretching space itself. What does this accelerated expansion mean for the far future? If dark energy continues its work, the universe will not only keep expanding, but will do so at an ever-increasing rate. Over tens of billions of years, galaxies beyond our local group will recede so far and fast that their light can no longer reach us, disappearing from view. Trillions of years from now, star formation in galaxies will peter out as the gas needed to form new stars is exhausted or locked away. Existing stars will age and die without replacements, and the night sky will gradually darken as galaxies lose their stars one by one. The Milky Way and Andromeda, by then long merged into a single huge galaxy, will find itself alone in the darkness, with no other galaxies left within view. Fast forward even further, to timescales scarcely fathomable. In perhaps 100 trillion years, 10 or 14 years, the last red dwarf stars will burn out, ending the era of starlight. The universe will enter its degenerate age, populated only by the remnants of stars, white dwarfs, neutron stars, and black holes, along with cold planets and diffuse gas. Collisions and decay processes will gradually disrupt many of the remaining systems. Planets might spiral into their dead suns or be flung into interstellar space. Over quadrillions and quintillions of years, black holes will dominate as the last massive objects. They too are not eternal. As Stephen Hawking theorized, black holes very slowly evaporate by emitting Hawking radiation. For a supermassive black hole, this process is extraordinarily slow, but given around 10 or 100 years or more, even the mightiest black holes will eventually evaporate to nothing. In that remote epoch, the universe will be extremely cold, thin, and dark. With no free energy left to fuel processes, it will have reached a state of maximum entropy, the heat death of the universe. All that will remain is a sparse sea of elementary particles and faint radiation, stretching through an ever-expanding emptiness. Time itself will lose much of its meaning in such a frozen, unchanging state. This, according to our best understanding, is the ultimate fate that awaits if no new physics intervenes. A cosmos that began in a blaze of light, ending in eternal night. Some theorists have considered alternative endings to this story. If dark energy were to grow stronger over time, it could eventually rip apart galaxies, stars, and even atoms in a catastrophic Big Rip. Conversely, if dark energy were to fade or reverse, gravity might one day pull the universe back together in a big crunch, causing a fiery collapse and perhaps a new rebirth. At present, however, observations favour an endless expansion leading to heat death, a slow dimming rather than a sudden cataclysm. It's a melancholy thought that the universe's story may end in darkness and silence. Yet we are living in a cosmically rich time, a time when stars still shine and life has the chance to flourish. We inhabit a universe that is still in its youthful stage compared to its long future. The fiery birth of the cosmos and its distant, quiet end serve as cosmic bookends to an epic tale, one that encompasses all that we know. And in that tale, for a brief moment, on at least one small planet, the universe became aware of itself. With the journey from the beginning of time to the ultimate future laid out before us, we can't help but feel a sense of perspective and wonder. We have witnessed the cosmos grow from a hot, dense speck to a vast expanse studded with galaxies, and learned how it might eventually fade away. All that remains now is to reflect on our place in this grand story, to consider what all of this means for us, the observers who ride a small world around an ordinary star in a remote corner of a galaxy. Our voyage through space and time leaves us with a profound perspective on our existence. We have journeyed from our Milky Way galaxy to the far reaches of the universe, from the birth of stars in glowing nebulae to the death of the cosmos in eternal night. In doing so, we've seen that our planet, our lives, and indeed all of humanity are part of something vast and ancient. The atoms in our bodies were forged in stars that died long before the earth formed. The calcium in our bones, the iron in our blood, these came from stellar furnaces and supernova explosions. We truly are made of star stuff, connected at the most fundamental level to the cosmos around us. Standing on our tiny world, orbiting an ordinary star, we look out into a universe of breathtaking grandeur. The scales of space and time we've encountered are humbling. Our Earth is a small, fragile haven in a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies. In the face of such immensity, our everyday concerns can seem insignificant. Yet it is precisely from our small world that we have been able to discover all these wonders. Through curious minds and ingenious tools, we have peered deep into the Milky Way, glimpsed distant galaxies billions of light years away, and unraveled the history of the universe from its fiery beginning to its far future. Knowing our place among the stars brings both humility and hope. On one hand, we see how tiny and fleeting we are, one species living on a speck of dust suspended in an endless expanse. On the other hand, we also see that we are participants in a magnificent cosmic drama. The elements that compose us were born in stellar hearts. The light that warms us was ignited in a star's core. We are children of the universe, and our very existence is tied to the stars. In a sense, the universe has become aware of itself through our eyes and minds. Our explorations also highlight the preciousness of our home. So far, amid all the planets we have found, Earth remains uniquely hospitable to life, a rare oasis in the cosmic desert. The pale blue dot that is our planet is the only home we know, a fact that underscores how important it is to cherish and protect it. As we marvel at the cosmos, we can also feel gratitude for our vantage point within it, a safe harbour from which we can observe and learn about the universe. The cosmic perspective reminds us that we are one people sharing one fragile world. Borders and divisions that loom large in daily life fade away when viewed against the backdrop of a galaxy. From a distant vantage, one would only see a single, pale blue world teeming with life. The realization of our planet's singularity in the vast darkness encourages a sense of unity and common destiny for humankind. We are the only known bearers of consciousness, the only known storytellers of the universe's tale. at least for now. As our journey comes to an end, we reflect on the incredible tapestry of existence spread out before us. We have witnessed stars being born and stars dying, peered into the heart of our galaxy, and voyaged beyond to other galaxies. We have contemplated black holes that challenge our understanding of physics, and pondered mysteries like dark matter and dark energy that hint at how much we have yet to learn. We saw planets around other suns, stirring the age-old question of whether we are alone, and we traced the universe's life story from its fiery inception to its quiet twilight, realizing the enormity of time and the impermanence of all things. In all of this, one theme resonates: connection. We are connected to the universe and to each other. Every atom in our bodies has cycled through cosmic processes, stretching back to the dawn of time. We share the same origin as the stars in the sky. When we look up at the Milky Way arching overhead, we are not just seeing distant lights. We are seeing our extended family, the cosmic ecosystem that gave rise to us. The sense of wonder instilled by the night sky has been with humanity since our earliest days. We have always looked up and felt something stir within us, a combination of curiosity, awe, and a yearning to connect with the cosmos. Now, armed with scientific knowledge, that wonder is only deepened. The more we learn about the universe, the more extraordinary and precious it becomes. The cosmos is not cold and indifferent. It is our home. We carry its history within us, and our destiny is entwined with its future. Under the quiet canopy of stars, as we contemplate the vastness around us, there is a gentle comfort in understanding our place. We are small, but we are part of this great story. Our minds can roam galaxies and eons, even as our bodies remain grounded on Earth. In that capability lies a quiet triumph. The universe has given rise to beings who can appreciate its beauty and seek to understand its mysteries. Our journey through space and time ends here, but the quest for knowledge and meaning goes on. The next time you step outside on a clear night, look up. See the starlight that has travelled across millions of years to reach your eyes. Feel the connection to the cosmos that surrounds you. We have travelled among stars, planets, and beyond, and returned home, illuminated by the knowledge that the same stardust fills our veins. In the silence of the night, beneath the glittering sky, we find our answer. We are not apart from the universe. We are a part of it. And as long as we continue to wonder and explore, the stars will never truly be beyond our reach.